History is filled with names, dates, and events. Ancient mysteries begin where those things run out. A structure survives, but no one remembers who built it. A city remains intact, but its disappearance was never recorded. A network of tunnels stretches beneath the ground. Yet no text explains why it exists. These are the moments where archaeology moves beyond history and into investigation. Every stone, artifact, and buried wall becomes a clue from a world that can no longer speak for itself. Sometimes the clues fit together, often they do not. And when they don't, they leave behind questions that can survive for centuries. Questions that continue to challenge researchers, inspire new discoveries, and remind us how much of the ancient world remains unknown. Vila de Leyva, Colombia. Hundreds of years before European astronomers brought telescopes to South America, an unknown group of engineers from the Muisca civilization erected dozens of stone pillars across a high-altitude valley. Today, archaeologists call the site El Infiernito. What appears at first glance to be a simple arrangement of stones may actually represent one of the most sophisticated astronomical systems ever built in pre-Columbian America. Spanish chroniclers first described the stone field during the 16th century after the conquest of the Muisca people. Systematic archaeological investigations began centuries later, revealing rows of standing stones, ceremonial structures, burials, and evidence that the site functioned as both a religious center and a possible astronomical observatory. Yet one question remains unresolved. How accurate was El Infiernito really? This is the greatest mystery of El Infiernito, and the reason the site is often compared to Stonehenge. The surviving stone columns are arranged in parallel rows extending across the landscape. Researchers discovered that several alignments correspond closely to the position of sunrise during the solstices and equinoxes. If intentional, this would mean that the builders could track the annual movement of the sun with remarkable precision. To understand the significance of this achievement, consider the challenge involved. The Earth's axis is tilted approximately 23.5 degrees. As a result, the sunrise position shifts continuously along the horizon throughout the year. Detecting this movement requires repeated observations over many years. A single observation is insufficient. Builders must establish fixed reference points, identify recurring patterns, and distinguish long-term cycles from seasonal variation. Modern observatories solve this problem using calibrated instruments. The builders of El Infiernito had none of these tools. No telescopes, no metal surveying equipment, no optical lenses, and no written trigonometric tables. Yet the stone alignments suggest that someone understood the movement of the sun well enough to transform astronomical observations into permanent architecture. The mystery becomes even deeper when considering the site's latitude. Located near 5 degrees north, seasonal changes in solar position are less dramatic than at higher latitudes. Detecting solstice positions is therefore more difficult than in places such as Stonehenge in England. Some archaeologists estimate that achieving reliable solar alignments would require observations spanning multiple decades. The builders may have recorded sunrise positions year after year, gradually refining the placement of each stone until a functioning solar calendar emerged. But no evidence has been discovered explaining exactly how this process worked. Did they use wooden sighting posts that later decayed? Did they employ shadow tracking methods similar to those used in ancient Egypt? Did generations of observers preserve astronomical knowledge through oral traditions? The stones remain silent. The arrangement of El Infiernito appears deceptively simple. In reality, creating long rows of aligned stones requires advanced surveying techniques. Even small errors accumulate rapidly over distance. A deviation of only 1 degree can shift a sightline by several meters across a long alignment. Modern engineers use transits, laser levels, GPS systems, and mathematical calculations. The Muisca possessed none of these technologies, yet the stones exhibit an organization suggesting careful planning rather than random placement. Experimental archaeologists have demonstrated that surprisingly accurate alignments can be produced using only ropes, wooden stakes, and observations of shadows cast by the sun. However, reproducing the precision potentially observed at El Infiernito remains challenging. The exact surveying methods employed by the builders remain unknown. Constructing a solar observatory requires enormous effort. Each stone had to be quarried, transported, positioned, and stabilized. The process demanded labor, planning, and social organization. Why invest such resources? One explanation involves agriculture. The Muisca economy depended heavily on crops such as maize, potatoes, quinoa, and beans. Accurate knowledge of seasonal cycles would have provided significant advantages for planting and harvesting. Another possibility involves religion. Throughout the ancient world, astronomy and spirituality were deeply connected. Egyptian temples, Maya observatories, and Mesopotamian ziggurats all incorporated celestial alignments into sacred architecture. El Infiernito may have served a similar purpose. The ability to predict solstices and seasonal transitions could have reinforced religious authority, transforming astronomical knowledge into political power. The largest surviving pillars are not as massive as the megaliths of Stonehenge, where some stones exceed 25 tons. Nevertheless, many El Infiernito pillars still weigh hundreds of kilograms or more. Transporting such stones without wheeled vehicles presents a substantial engineering challenge. The Muisca had no horses, oxen, or large draft animals before European contact. Human labor alone would have been responsible for moving the stones. Archaeologists propose several possibilities, including wooden rollers, sledges, rope systems, earthen ramps, and collective labor teams. All are technically plausible, yet no direct archaeological evidence has revealed which method was actually used. The engineering process remains largely invisible. Spanish accounts describe the Muisca as possessing one of the most sophisticated calendrical systems in pre-Columbian South America. Historical records suggest they tracked complex cycles of time and maintained an advanced numerical system. This is particularly significant because astronomical observation and mathematics are inseparable. A functioning solar calendar requires counting days, recognizing recurring patterns, and predicting future events based on previous observations. The existence of El Infiernito suggests a body of mathematical knowledge that once existed but largely vanished following the Spanish conquest during the 16th century. Today, archaeologists can identify the results of that knowledge. The knowledge itself is mostly gone. For decades, researchers debated the site's primary purpose. The astronomical interpretation is compelling, but El Infiernito also contains evidence of ritual activity, ceremonial practices, and burials. Some stone pillars possess obvious symbolic and fertility-related characteristics. Others appear associated with sacred spaces rather than purely observational functions. This raises an important possibility. What if the site was never intended to be only an observatory? Many ancient monuments served multiple functions simultaneously. Stonehenge functioned as a ceremonial center, burial site, and astronomical marker. The Temple of Karnak incorporated both religious and solar alignments. Maya observatories combined political, ceremonial, and scientific functions. El Infiernito may belong to this same category, a place where astronomy, religion, politics, and social organization merged into a single system. Was El Infiernito primarily an astronomical observatory, or was astronomy simply one part of a much larger system of religion and power? Jinsha site is one of the greatest archaeological mysteries ever discovered in China. Beneath modern Chengdu in Sichuan province lies evidence of an advanced Bronze Age civilization that mastered technologies still not fully understood today. The site was discovered accidentally in 2001 when construction workers excavating land in western Chengdu uncovered thousands of ancient artifacts. Archaeologists quickly realized they had found the lost center of the ancient Shu civilization, a culture that flourished more than 3,000 years ago and emerged shortly after the mysterious decline of Sanxing Duai. What they uncovered raised far more questions than answers. One of the first mysteries surrounding Jinsha concerns its very existence. For decades, Sanxing Dui had been considered the primary center of the ancient Shu kingdom. Then, sometime around the 12th century BCE, Sanxing Duai appears to have been abandoned. Archaeological evidence suggests no large-scale military destruction, and there are no records describing a foreign invasion. Yet the political and religious center of the civilization shifted approximately 40 kilometers south to Jinsha. The transition remains poorly understood. Some researchers propose that a massive earthquake altered regional river systems. Geological studies have identified evidence of seismic activity in Sichuan during the Late Bronze Age. Others suggest catastrophic flooding may have damaged critical infrastructure and agricultural systems, while another theory proposes a planned relocation directed by ruling elites. The problem is that none of these explanations fully account for the available evidence. Instead of societal collapse, archaeologists see remarkable continuity. Religious symbols, artistic styles, jade traditions, and ritual practices all appear to continue at Jinsha. It looks less like a civilization disappearing and more like a civilization moving. But why? More than 3,000 years later, the answer remains unknown. The most astonishing mystery at Jinsha involves gold. Thousands of years before modern machinery, the craftsmen of Jinsha produced gold artifacts displaying a level of precision that continues to impress modern metallurgists. The most famous example is the sun and immortal bird's gold ornament. This extraordinary object measures approximately 12.5 centimeters in diameter and weighs only about 20 grams. The gold sheet from which it was made is roughly 0.2 millimeters thick. To appreciate how remarkable this is, consider that a typical credit card is around 0.76 millimeters thick. The Jinsha ornament is less than 1/3 of that thickness, yet despite its delicate structure, the artifact contains highly precise geometric patterns. A central sun surrounded by 12 rays is enclosed by 4 birds flying in a perfectly balanced circular arrangement. Creating such an object required extraordinary control over metal deformation. Modern goldsmiths understand that repeatedly hammering gold causes work hardening. The metal becomes increasingly brittle and eventually cracks unless carefully reheated through annealing. The Jinsha craftsmen clearly understood these principles in practice, despite leaving behind no written explanation. Researchers believe the object was produced through repeated cycles of hammering, heating, and reshaping. However, the exact techniques remain uncertain because the specialized tools used in the process have never been conclusively identified. The precision becomes even more remarkable when compared with contemporary civilizations. During roughly the same period, many Bronze Age societies across Eurasia produced impressive gold ornaments. The elites of Mycenaean Greece possessed gold masks and jewelry, while ancient Egypt produced sophisticated gold artifacts for pharaohs. Yet, the Jinsha ornament demonstrates a unique combination of thinness, symmetry, and symbolic complexity rarely observed elsewhere. Microscopic analysis reveals extremely clean edges and carefully controlled perforations. Some researchers argue that achieving such consistency would have required generations of accumulated technical knowledge. Where did this knowledge originate? No one knows. Even more puzzling is the scale of gold production. Jinsha has yielded hundreds of gold artifacts, suggesting access to significant quantities of raw material. Yet evidence for large-scale mining operations directly associated with the site remains limited. This raises another question. How did the Shu civilization obtain so much gold? Was it extracted locally from Sichuan's river systems? Did long-distance trade networks transport precious metals across ancient China? Or did Jinsha control resource zones that have not yet been identified? The answers remain elusive. Perhaps the greatest mystery is that this technological tradition eventually vanished. The artifacts survived, but the knowledge did not. Another mystery emerged when archaeologists began excavating ritual pits. They discovered enormous quantities of ivory. Thousands of elephant tusk fragments have been recovered from the site, representing one of the largest concentrations of ivory ever found in Bronze Age China. The scale is astonishing. Some pits contained stacks of tusks placed in deliberate ceremonial arrangements alongside gold, jade, and stone artifacts. The question is simple. Where did the elephants come from? Modern Chengdu is not known for large elephant populations. Climate reconstructions suggest environmental conditions may have been somewhat different 3,000 years ago, but the sheer quantity of ivory remains difficult to explain. Some scholars propose that elephants once inhabited parts of Sichuan. Others suggest the tusks arrived through extensive trade networks stretching hundreds or even thousands of kilometers. If the second explanation is correct, Jinsha may have been connected to one of the most sophisticated exchange systems in Bronze Age East Asia. Jinsha also produced large numbers of jade artifacts. Unlike gold, jade is extremely difficult to work. High-quality jade possesses hardness values approaching those of hardened steel, meaning ancient craftsmen could not simply carve it with ordinary metal tools. Instead, they likely relied upon abrasive drilling and grinding techniques. Yet many Jinsha artifacts exhibit remarkably smooth surfaces, symmetrical shapes, and precisely drilled holes. Experimental archaeologists have attempted to reproduce similar objects using ancient methods. The results often require dozens or even hundreds of labor hours for a single piece. This creates an important question. How many skilled specialists existed within Jinsha society? The craftsmanship suggests a highly trained workforce supported by an organized economy capable of sustaining artisans who are not directly involved in food production. In other words, the technological achievements point toward a level of social complexity that archaeologists are still trying to understand. The famous gold ornament may contain another mystery: astronomy. The artifact's design includes 4 birds circling a central sun surrounded by 12 rays. The number 12 appears repeatedly throughout ancient timekeeping systems around the world. Ancient Mesopotamian calendars divided the year into 12 months, and similar numerical patterns later emerged throughout East Asia. Some researchers have proposed that the Jinsha symbol encoded astronomical observations or represented a solar calendar. Others argue that it was purely religious. The problem is that the Shu civilization left no deciphered writing system capable of explaining the meaning directly. As a result, archaeologists can study the symbol but cannot fully read its message. 3,000 years later, its true purpose remains unknown. Every artifact discovered at Jinsha points towards sophisticated administration. Gold had to be acquired, jade had to be transported, ivory had to be collected, craftsmen had to be trained, and ritual ceremonies had to be organized. All of this required logistics, planning, and leadership. Yet archaeologists have found surprisingly little direct evidence explaining how the system functioned. No extensive written archives survive and no detailed administrative records exist. The civilization clearly possessed advanced organizational capabilities, but the mechanisms behind them remain hidden. El Perutal, hidden within the mountains of Huila in southern Colombia, contains a mystery that should not exist. More than 1,000 years after its craters disappeared, traces of red, yellow, black, and white paint still cling to its stone statues. While the colours of most ancient monuments vanished centuries ago, the pigments of El Perutal survived. El Perutal forms part of the larger San Agustin Archaeological Park, a UNESCO World Heritage Site. Archaeological investigations throughout the 20th century revealed a ceremonial complex containing tombs, artificial mounds, and some of the only known polychrome statues from the ancient San Agustin civilization. These discoveries transformed El Perutal into one of the most important archaeological mysteries in South America. The greatest mystery of El Perutal is not the statues themselves, but the paint. Throughout history, colour has proven surprisingly fragile. The vibrant pigments that once decorated Greek temples have almost entirely disappeared. Many Roman sculptures lost their original paint layers, and even murals preserved inside protected structures often suffer severe degradation after centuries of exposure. Yet, at El Perutal, pigments remain visible after approximately 1,000 to 1,500 years. The statues display traces of red, yellow, black and white coloration. Scientific analysis suggests that the colours were likely derived from natural mineral sources. Red pigments may have originated from iron oxides similar to hematite. Black pigments may have contained manganese compounds or charcoal-based materials. Yellow pigments were likely produced from iron-rich minerals, while white pigments may have involved clay or mineral-based substances. The real mystery is not the source of the pigments, but their survival. El Perutal lies in a tropical environment characterized by rainfall, humidity, biological activity, and significant temperature fluctuations. Such conditions normally accelerate weathering. Rainwater penetrates stone surfaces, organic growth damages pigments, and ultraviolet radiation breaks down molecular structures. In many comparable environments, ancient paint survives only in microscopic traces. Yet portions of the El Perutal pigments remain visible to the naked eye. Researchers still cannot fully reconstruct the original manufacturing process. What binding agents were used? How were the pigments attached to the stone? Was the stone chemically prepared before painting? Were multiple protective layers applied? No surviving document answers these questions. The situation resembles other ancient technological mysteries. Scientists studying Roman concrete eventually discovered that volcanic ash contributed to the material's remarkable durability, while researchers investigating Egyptian pigments found sophisticated chemical knowledge behind supposedly simple colours. El Perutal may represent another example of ancient materials, science whose underlying principles remain only partially understood. The statues stand as physical proof that the San Agustin people possessed practical knowledge of mineral chemistry, surface preparation, and long-term durability. The results survived, but the instructions disappeared. Most people imagine ancient stone monuments as monochrome objects, yet archaeology increasingly reveals the opposite. Ancient Greek temples were painted, Roman statues were painted, and Egyptian monuments were painted. El Perutal demonstrates that the San Agustin civilization followed a similar tradition. The statues were not merely carved, they were transformed into multicolored visual displays designed to communicate symbolic messages. This required several technological steps. First, suitable stone had to be selected and shaped. Second, surfaces needed preparation to receive pigments. Third, colors had to be produced from mineral resources. Fourth, pigments had to be applied in a manner capable of surviving environmental exposure. Each step required specialized knowledge. Modern conservators often spend years studying the interaction between pigments and stone surfaces. The artisans of El Perutal achieved comparable results without modern chemistry, microscopes, or laboratory equipment. How they perfected the process remains uncertain. The most famous statues at El Purutal are often interpreted as representations of life and death. The problem is that nobody knows for certain. The figures combine human and animal characteristics. Some display jaguar-like features, while others appear to incorporate symbolic elements associated with spiritual transformation. This ambiguity is one of the defining characteristics of San Agustin art. The civilization left no deciphered writing system. Unlike the Maya, whose inscriptions preserve historical records, the San Agustin people left primarily stone monuments. As a result, archaeologists must interpret symbolism without textual explanations. Were the figures gods? Were they ancestors? Were they rulers transformed into supernatural beings? Or were they shamans mediating between the physical and spiritual worlds? The statues remain silent. El Purutal was not simply a collection of sculptures. The site formed part of a carefully engineered ceremonial landscape. Archaeologists discovered artificial mounds, burial structures, retaining systems, pathways, and monument platforms integrated into the surrounding terrain. Creating such a landscape required substantial labour. Workers moved enormous quantities of soil to construct elevated areas. Slopes had to be stabilised, drainage systems needed management, and burial chambers had to be protected from collapse. These activities reveal a level of organisation far beyond what casual observers might expect. Modern earth-moving equipment can reshape landscapes in hours, but ancient builders relied entirely on human labour. The scale of modification suggests coordinated planning over extended periods. Who directed these projects remains unknown. The statues themselves present another engineering puzzle. Many San Agustin sculptures weigh several tons, and some stand more than 4 meters tall. Transporting such objects would challenge even modern crews operating in rugged mountain environments. The terrain surrounding El Purutal consists of hills, valleys, and steep slopes. No surviving roads reveal the exact transportation routes. No ancient diagrams explain the process, and no written instructions survive. Researchers generally believe that teams of workers moved the stones using ropes, wooden rollers, sledges, and carefully organised labour. The problem is that the details remain speculative. Ancient societies across the world repeatedly solve transportation challenges that continue to impress engineers today. The builders of Stonehenge moved stones weighing up to 25 tons across hundreds of kilometres. Egyptian workers transported granite blocks exceeding 60 tons, and in Peru, Inca builders moved massive masonry elements across mountainous landscapes. El Purutal belongs to this tradition of unexplained logistical achievement. The statues exist because the problem was solved. How it was solved remains uncertain. Perhaps the strangest mystery is that so much survives and yet so little is known. The broader San Agustin region contains more than 500 statues, numerous tombs, ceremonial structures, and extensive archaeological remains. This represents centuries of cultural activity, yet the people responsible left no readable historical record. Their language vanished, their political system vanished, their names vanished, and their technical manuals vanished. What remains are the products of their knowledge. Archaeologists can measure the monuments, analyze the pigments, map the structures, and reconstruct construction sequences. But the intellectual framework behind the civilization remains largely invisible. This creates a paradox. The evidence demonstrates significant expertise in sculpture, engineering, landscape modification, and materials technology. Yet the civilization itself remains one of the least understood major archaeological cultures of pre-Columbian South America. What do you think made the pigments of El Purutal survive for more than 1,000 years? Was it a lost painting technology, a unique combination of minerals, or knowledge that has completely vanished from history? Share your thoughts in the comments below. North Yorkshire, England. Along a remote stretch of cliffs facing the North Sea, an industry emerged in the 17th century that produced one of the most valuable chemical substances in Europe. The mystery is not what they made. The mystery is how they knew where to find it. The remains of Yorkshire's alum works were documented throughout the 18th and 19th centuries, but systematic archaeological investigation accelerated during the 20th century. Researchers uncovered massive burning platforms, extraction pits, reservoirs, stone tanks, transport routes, and industrial waste deposits stretching for kilometres along the coastline. These ruins revealed that North Yorkshire once hosted one of the largest chemical industries in Europe before the Industrial Revolution. This is the greatest mystery of all. Alum, chemically known as hydrated potassium aluminum sulfate, was one of the most important industrial chemicals in pre-industrial Europe. It was essential for fixing dyes in textiles, preserving leather, manufacturing medicines, and supporting numerous crafts. During the 16th century, Europe depended heavily on alum imported from Italy, particularly from the papal-controlled deposits at Tolfa. Then something remarkable happened. Around the late 16th century, English entrepreneurs discovered that the dark Jurassic shale exposed along the cliffs of North Yorkshire contained the ingredients necessary to manufacture alum. The question that continues to puzzle historians is simple. How did they know? The Yorkshire coast contains millions of tons of black shale, and most of it appears unremarkable. To the untrained eye, it looks no different from countless other rock formations across Britain. Yet hidden within specific layers were sulfur-bearing minerals, particularly pyrite, capable of producing the chemical reactions required for alum production. No geological surveys existed, no chemical laboratories existed, and no modern mineral analysis existed, yet someone identified the correct rock. One theory suggests that English agents secretly obtained industrial knowledge from Italy. Historical records indicate that experienced alum workers from the continent may have been recruited to England despite efforts by foreign powers to protect their monopoly. Another theory argues that local observers noticed similarities between Yorkshire shale and alum-bearing rocks described elsewhere in Europe. Neither explanation fully solves the mystery. Finding a useful rock formation is one challenge, but identifying thousands of hectares of productive shale among vast coastal exposures is another. Modern mining companies employ geologists, geochemical testing, satellite imagery, and drilling programs. The first Yorkshire alum producers had none of these tools. The situation is comparable to finding a hidden copper deposit without geology, locating petroleum without seismic surveys, or identifying uranium without radiation detectors. Somehow, knowledge existed before the science needed to explain it. Even today, historians cannot reconstruct the exact process through which Yorkshire's alum deposits were first recognised. After extraction, the shale underwent a process that appears astonishing even by modern standards. Workers piled enormous quantities of rock into vast mounds, sometimes reaching several meters in height and extending across large areas. These piles were then ignited and allowed to burn continuously, not for days, not for weeks, but for months. Historical accounts suggest that some burning cycles lasted between 6 and 12 months before completion. The objective was to oxidize pyrite contained within the shale. During combustion, sulfur compounds reacted with oxygen, generating sulfuric acid and initiating complex chemical transformations necessary for alum production. The mystery lies in control. Modern industrial roasting operations rely upon thermometers, airflow monitoring, automated systems, and chemical analysis. Yorkshire workers possessed none of these technologies. If temperatures became too low, reactions would remain incomplete. If temperatures became too high, valuable compounds could be destroyed. Yet generation after generation managed to achieve the desired result. Archaeological evidence indicates that workers carefully managed ventilation pathways within the burning heaps. However, researchers still debate exactly how temperatures were monitored and controlled. Much of this expertise appears to have been transmitted orally and vanished when the industry declined. Perhaps the most fascinating aspect of the Yorkshire alum industry is that it operated successfully before the scientific revolution fully explained the processes involved. The first commercial alum works appeared decades before modern chemistry emerged as a formal scientific discipline. Workers understood procedures, but they did not necessarily understand molecules. They understood outcomes, but they did not understand atomic structure. They knew which materials to combine, how long to burn the shale, how to process solutions, and when crystallization was complete. But concepts such as oxidation reactions, molecular bonds, and chemical equilibrium remained centuries away. This situation resembles other technological mysteries throughout history. Roman engineers produced durable concrete without understanding modern materials science. Medieval blacksmiths manufactured Damascus steel without knowledge of crystallography. The builders of the Antikythera mechanism created an analog computer nearly 2,000 years before modern mechanical engineering emerged. Yorkshire alum workers belong to the same tradition of practical expertise, exceeding contemporary scientific theory. Once roasting was complete, the shale had to be processed using large quantities of water. The solution sounds simple, but the reality was not. Many alum works occupied steep coastal locations where terrain presented major engineering challenges. Water had to be collected, directed, stored, and distributed across multiple processing stages. Archaeologists have identified extensive systems including reservoirs, channels, settling tanks, leaching pits, and evaporation facilities. Gravity performed much of the work. Instead of relying upon pumps, engineers designed layouts that allowed liquids to move naturally through successive stages of production. This required an understanding of gradients, flow rates, storage capacity, and hydraulic behavior. Some industrial complexes covered several hectares and processed thousands of tons of material annually. Their hydraulic sophistication rivals certain mining operations of later centuries. Yet no detailed engineering manuals survive. The physical structures remain, but the design logic behind them often does not. One of the most unusual aspects of alum production involved an ingredient found in virtually every community: human urine. Historical records indicate that urine was collected and incorporated into stages of the manufacturing process. To modern observers, this seems bizarre, but chemically it makes sense. Urine contains ammonia-producing compounds that influence reactions within processing solutions. The remarkable detail is that workers recognized its usefulness centuries before modern biochemistry explained why it worked. Communities sometimes participated in collection programs supplying industrial facilities with raw materials. This created a chemical supply chain based on empirical observation rather than scientific understanding. People knew the method worked, but few could explain the underlying chemistry. Yorkshire's alum industry operated on a vast scale. Millions of tons of shale were quarried, transported, burned, washed, and refined long before modern machinery existed. Workers extracted rock from coastal cliffs, moved it across difficult terrain, maintained burning heaps and hydraulic systems, and processed chemical solutions. The ruins reveal the industry's immense scale, but many details of how it functioned remain unknown. How do you think the first producers discovered that Yorkshire shale could be transformed into alum without modern science? Tongoni Ruins, on the coast of Tanga in northeastern Tanzania, preserves one of the greatest unsolved technological mysteries of the medieval Indian Ocean world, a civilization that mastered ocean navigation, coral stone engineering, and international trade, yet left behind almost no explanation of how it achieved them. The ruins became known to modern researchers during the colonial period and were later investigated by archaeologists studying the Swahili coast. Excavations revealed a large medieval settlement containing a mosque, more than 40 pillar tombs, imported ceramics from China and the Middle East, and evidence of long-distance maritime trade dating mainly between the 14th and 15th centuries. The first mystery begins with the buildings themselves. Tongoni was constructed primarily from coral rag, a fossilized limestone formed from ancient coral reefs. At first glance, coral stone appears to be a poor construction material. It is porous, vulnerable to salt penetration, and exposed continuously to tropical humidity, seasonal monsoon rains, and coastal erosion. Yet portions of Tongoni's structures have survived for more than 5 centuries. This durability raises important engineering questions. Modern material scientists understand that coastal environments are among the most destructive settings for masonry architecture. Salt crystals expand inside microscopic pores, gradually fracturing stone from within. Wind-driven moisture accelerates chemical weathering, while temperature fluctuations create repeated cycles of expansion and contraction. Many stone buildings constructed in similar marine environments deteriorate rapidly without constant maintenance. The builders of Tongoni somehow developed techniques that dramatically slowed this process. Archaeologists have identified carefully cut coral blocks fitted together using lime-based mortars. The production of lime itself required considerable technical knowledge. Coral or limestone had to be heated to temperatures exceeding 800 degrees Celsius, converted into quicklime, mixed with water, and transformed into a durable binding material. The exact composition of many Swahili mortars remains poorly understood. Some researchers suspect that local craftsmen developed specialized mixtures adapted to coastal conditions. If true, this would place them alongside other ancient civilizations that discovered advanced construction formulas, such as Roman engineers whose maritime concrete survived nearly 2,000 years in seawater. The structures remain, but the knowledge behind them largely vanished. Tongoni contains one of the largest concentrations of pillar tombs ever discovered on the East African coast. Some rise several meters above ground level and dominate the surrounding landscape. At first glance, they appear simple, but in reality they represent significant engineering achievements. Large quantities of coral stone had to be quarried, shaped, transported, and assembled with precision. The builders had to ensure that the tall vertical structures remained stable despite seasonal storms and centuries of weathering. The challenge becomes even more remarkable when considering the available technology. No cranes have been discovered, no lifting machines survive, and no construction manuals exist. Researchers therefore face a fundamental question. How were these monuments erected? Similar mysteries appear elsewhere in the ancient world. The builders of the Egyptian obelisks, the Moai of Easter Island, and the stone monuments of Great Zimbabwe all developed methods for moving and positioning massive materials with limited technology. Tongoni may represent a Swahili version of the same phenomenon. The monuments demonstrate capabilities that clearly existed, yet the procedures behind those capabilities remain largely unknown. The third mystery concerns economics and logistics. Excavations at Tongoni have recovered imported ceramics from China, Persian Gulf pottery, glass beads, and other foreign goods. These discoveries demonstrate that the settlement participated in a trade network stretching across thousands of kilometers. The scale of that network is difficult to exaggerate. A ceramic vessel manufactured in China could travel through multiple ports across the South China Sea, pass through Southeast Asia, cross the Indian Ocean, reach Arabian merchants, and eventually arrive on the East African coast. This system existed centuries before modern shipping companies, satellite navigation, weather forecasting, or international logistics software. Yet it functioned successfully. For Tongoni to participate, local merchants required sophisticated knowledge of commerce, storage, scheduling, negotiation, and maritime transportation. The ruins suggest a surprisingly interconnected medieval world, but they also reveal a major gap in our understanding. We know the trade occurred, yet we do not fully understand the organizational systems that made it possible. Every successful coastal settlement faces a challenge: freshwater. Saltwater surrounded Tongoni, but saltwater cannot sustain a population. A settlement engaged in international trade required drinking water, water for cooking, water for construction activities, and water for daily life. The problem becomes even more complicated during dry seasons. Many ancient civilizations solved similar challenges through aqueducts, reservoirs, cisterns, wells, and underground channels. The Romans built vast hydraulic systems, Persian engineers created qanats, and Nabatean builders developed sophisticated desert water networks. The exact solution employed at Tongoni remains uncertain. Researchers have identified evidence of water management practices, but the complete system has never been reconstructed. Did the inhabitants rely on deep groundwater, rainwater harvesting, seasonal storage facilities, or a combination of multiple technologies? The archaeological evidence remains incomplete. As a result, one of the most important engineering systems that sustained the settlement is still only partially understood. This is perhaps the greatest mystery of all. Tongoni existed because of the sea. Without navigation, there would have been no trade. Without trade, there would have been no prosperity. Without prosperity, there would have been no city. The Indian Ocean is one of the largest bodies of water on Earth, covering approximately 70 million square kilometers. Crossing it successfully required far more than courage, it required science. For centuries, Swahili sailors traveled between East Africa, Arabia, Persia, and India. Some voyages exceeded thousands of kilometers. Yet these journeys were conducted without GPS, radar, radio communication, or modern navigational instruments. The question is simple: how did they do it? Historical evidence suggests that sailors relied heavily on monsoon winds. These seasonal wind systems reverse direction approximately every 6 months. During one season, winds favor travel toward India and Arabia, while during another they favor the return voyage toward East Africa. Understanding this cycle alone required generations of observation. But wind knowledge was only the beginning. Navigators likely used stars as reference points. They monitored the rising and setting positions of celestial objects and observed wave patterns, currents, cloud formations, bird migrations, and changes in water color. This knowledge was extraordinarily valuable, and almost all of it disappeared. Unlike European maritime powers that later produced extensive written manuals, charts, and navigational texts, much of the Swahili maritime tradition appears to have been transmitted orally. When oral traditions break, knowledge can vanish with astonishing speed. The situation resembles other famous technological losses in history. The mechanism behind the Antikythera device disappeared for over 1,000 years. The precise manufacturing techniques of Damascus steel became obscure, and the full formula of Roman maritime concrete was forgotten. Tongoni may represent another example. A sophisticated navigational system once connected East Africa to half the known world. Today, archaeologists can prove that the voyages occurred, but they cannot fully reconstruct the knowledge that made them possible. The sailors succeeded, yet their science vanished. Only a fraction of Tongoni has been thoroughly investigated. This creates another fascinating possibility. The visible ruins may represent only a small percentage of the original settlement. entire residential districts may remain buried, workshops could still lie underground, and storage facilities, harbour-related structures and industrial areas may never have been excavated. Ground-penetrating radar surveys at archaeological sites around the world have repeatedly revealed hidden architecture invisible from the surface. Similar discoveries transformed understanding of cities such as Angkor, Pompeii and Teotihuacan. Tongoni may hold comparable surprises. Future excavations could dramatically change what historians believe about the scale and sophistication of the settlement. Kayola Ruins, Bagamoyo, Tanzania. 600 years ago, builders on the East African coast created stone monuments from coral reefs, produced industrial quantities of lime without modern furnaces, and constructed structures that still survive today. Yet the technology behind their achievements remains only partially understood. The ruins were documented during the colonial era and later investigated through archaeological surveys throughout the 20th century. Excavations revealed mosques, tombs, imported ceramics, coins, and evidence of a prosperous Swahili settlement connected to the Indian Ocean trade network. The first mystery begins with the construction material itself. Unlike the great monuments of Egypt, Greece, or Rome, Kayola was not built from granite, limestone, or marble. Its builders used fossilized coral stone extracted from ancient reef formations along the coast. Coral stone presents a serious engineering challenge. It is porous, relatively soft when freshly quarried, and highly vulnerable to moisture, salt, and biological weathering. Modern coastal engineers understand how difficult it is to construct durable structures in marine environments because salt penetration gradually weakens most building materials. Yet many walls at Kayola have survived for more than 6 centuries. Archaeologists studying Swahili architecture have found that coral stone was cut into blocks and assembled with lime mortar. However, the exact methods used to select, cure, and prepare the material remain uncertain. Some walls display weathering rates that differ dramatically from neighbouring structures. In certain sections, the masonry remains remarkably stable despite centuries of exposure to tropical humidity and seasonal rainfall. The question remains unanswered. Did the builders possess practical knowledge about material durability that has since been lost? The greatest technological mystery at Kayola concerns lime production. Every major stone structure at the site depended on lime mortar. Without it, the coral blocks could not have been bonded into stable walls, arches, and foundations. Producing lime sounds simple until the science is examined. Coral consists primarily of calcium carbonate. To transform it into quicklime, builders had to heat the material to temperatures approaching 850 to 1000 degrees Celsius. This process drives carbon dioxide from the stone and creates calcium oxide, the foundation of lime mortar. Modern chemistry explains the reaction. Calcium carbonate transforms into calcium oxide and carbon dioxide. The problem is scale. A single mosque might require many tons of mortar. Multiple mosques, tombs, and public structures would require far more. Producing such quantities would demand enormous amounts of fuel and carefully controlled firing conditions. This creates a puzzle. Where did the fuel come from? How were furnaces designed? How did workers maintain temperatures near 900 degrees Celsius for extended periods? How was quality controlled across multiple batches? Ancient Roman builders solved similar problems through vast industrial lime kilns spread across the empire. Medieval European builders developed sophisticated kiln systems to support cathedral construction. Yet the kiln infrastructure associated with Kayola remains poorly understood. Researchers know the lime existed because the buildings still stand. What they do not fully understand is the industrial process that produced it. Some specialists suggest that generations of craftsmen accumulated practical knowledge through experimentation. Others argue that technological expertise may have arrived through trade connections linking East Africa to Arabia, Persia, and India. Either way, the knowledge disappeared. The monuments remain, the manufacturing system that created them does not. Among the most distinctive structures at Cayole are its pillar tombs. These monuments consist of tomb chambers topped by tall stone pillars that rise dramatically above the surrounding landscape. From an engineering perspective, the pillars present several questions. They provide little structural support, require additional labor, and increase construction complexity. Yet builders repeatedly chose to include them. Some researchers believe they functioned as status symbols marking elite burials. Others suggest they served as navigational landmarks visible to sailors approaching the coast. Another theory links them to architectural traditions originating in the wider Islamic world. No explanation fully accounts for their distribution or design. What remains clear is that constructing tall vertical monuments from coral masonry required considerable understanding of balance, load distribution, and long-term stability. Artifacts recovered from Cayole reveal connections extending thousands of kilometers beyond East Africa. Imported ceramics, glass beads, and trade goods indicate participation in the vast Indian Ocean commercial network. During the medieval period, merchants traveled between East Africa, Arabia, Persia, India, and even China. These routes moved not only goods but also ideas. Technological knowledge may have traveled alongside merchants, including construction techniques, kiln designs, architectural principles, and material processing methods. The challenge is determining exactly how knowledge moved. Did Swahili builders independently develop their engineering techniques? Did they adapt foreign technologies to local materials? Or did entirely new solutions emerge from the interaction of multiple cultures? The archaeological evidence provides clues but not definitive answers. The surviving ruins create a misleading impression. Visitors often assume they are seeing the ancient settlement itself. In reality, archaeologists suspect that most of the city has vanished. Stone structures represent only the most durable components of a much larger urban environment. Houses built from timber, earth, palm materials, and other organic resources may have disappeared completely. This creates a major archaeological problem. If most of the settlement no longer exists, how large was Cayole? How many people lived there? How was labor organized? How are building projects coordinated? The surviving monuments may represent only a fraction of the original city. The rest remains hidden beneath centuries of environmental change. Every successful settlement requires reliable access to fresh water. Cayole occupied a coastal environment where saltwater intrusion constantly threatened groundwater supplies. Maintaining a permanent population would have required effective water management, yet evidence for these systems remains limited. Researchers continue to investigate how inhabitants collected, stored, and protected freshwater resources. The challenge resembles problems faced by other coastal civilizations throughout history. From Arabian ports to Indian Ocean trading centers, successful communities depended upon sophisticated solutions to water scarcity. Cayole almost certainly possessed similar systems, but the details remain elusive. Kardaki Temple is one of the strangest ancient Greek temples ever discovered. Standing on the island of Corfu in western Greece, overlooking the Ionian Sea, the structure appears at first glance to be a typical archaic Greek sanctuary. Yet the deeper archaeologists investigate its remains, the more unusual it becomes. Built around the 6th century BCE, Kardaki challenges some of the fundamental assumptions about how Greek temples were designed and constructed. Even today, more than 2,500 years later, researchers continue debating why its builders abandoned architectural conventions followed throughout the Greek world and how they achieved a level of geometric precision that remains difficult to fully explain. The temple became known to modern archaeology in the early 19th century when portions of the structure were identified near the famous Kardaki Spring on Corfu. Excavations revealed the foundations and architectural fragments of an ancient temple that differed significantly from other Greek sanctuaries of the same era. What initially appeared to be a routine archaeological discovery gradually evolved into a puzzle involving engineering, geometry, geology, and lost architectural knowledge. The first mystery concerns the temple's highly unusual architectural design. Most Greek temples built during the Archaic period followed established Doric conventions. Structures such as the Temple of Hera at Olympia and the early temples at Paestum incorporated triglyphs and metopes as part of the characteristic Doric entablature. Kardaki, however, appears to have omitted these features entirely. This may seem like a minor decorative difference, but from an engineering perspective it is significant. Triglyphs and metopes were not merely ornamental, they formed part of a structural system that distributed loads from the roof into the supporting columns below. The absence of these elements raises difficult questions. Did Kardaki represent an experimental architectural tradition? Was it influenced by Ionic construction techniques? Or did its builders possess a local engineering method that disappeared from history? Some scholars have suggested that Kardaki may represent one of the earliest examples of architectural innovation that blurred the distinction between the Doric and Ionic orders. If true, the temple provides evidence that ancient Greek architecture evolved through experimentation rather than strict adherence to established formulas. The second mystery involves the temple's location. Kardaki was constructed immediately beside a natural spring. Modern engineers generally avoid placing massive stone structures on water-saturated ground because groundwater can destabilize foundations through erosion, settlement, and seasonal movement. Yet the temple survived for centuries in precisely such an environment. Hydrological studies demonstrate that groundwater significantly affects soil mechanics. When water content increases, the bearing capacity of many soils decreases, creating conditions that can lead to uneven settlement. Ancient builders obviously lacked modern geotechnical instruments, yet Kardaki's foundations appear to have been sufficiently stable to support a substantial stone structure for generations. How did they evaluate the ground conditions? Did they understand subsurface drainage? Did they incorporate hidden foundation systems now lost to erosion? Similar questions surround other ancient sites located near water sources, including certain sanctuaries at Delphi and Didyma. Kardaki suggests that Greek builders possessed practical geological knowledge that was never formally recorded. The third mystery concerns the transportation and assembly of construction materials. Although the temple was built primarily from local limestone, moving large stone blocks remained a formidable engineering challenge. Individual architectural elements may have weighed several tons. Without cranes, hydraulic machinery, or iron industrial equipment, ancient builders relied entirely upon human labor, animals, ropes, timber frameworks, and mechanical principles. Experimental archaeology has shown that teams using ropes and wooden sledges can move stones weighing multiple tons. However, successfully transporting, lifting, positioning, and aligning hundreds of architectural components requires extraordinary organization. Researchers studying Greek temple construction often compare these achievements with those of Egyptian pyramid builders and Roman engineers. In every case, the surviving monuments demonstrate capabilities far beyond what many people assume was possible in antiquity. The fourth mystery involves seismic resilience. Corfu lies within a tectonically active region, influenced by interactions between the African and Eurasian plates. Throughout historical time, Greece has experienced numerous significant earthquakes. Modern seismic hazard maps continue to classify portions of the region as vulnerable to strong ground motion. Yet portions of Kardaki's foundation survive despite centuries of seismic activity. This raises the possibility that ancient builders unintentionally, or perhaps intentionally, incorporated features that improved earthquake resistance. Similar discussions surround the Parthenon in Athens, whose precisely fitted stone blocks help dissipate stress during seismic events. Some engineers have noted that ancient Greek masonry occasionally behaved as a flexible system rather than a rigid one. If Kardaki employed comparable principles, it may represent an early example of earthquake-aware construction. The fifth mystery is perhaps the most astonishing of all, the temple's extraordinary geometric precision. When archaeologists analysed the surviving foundations and column spacing, they discovered evidence of remarkable proportional consistency. Distances between structural elements appear to follow carefully planned mathematical relationships. The builders were not simply stacking stones, they were implementing a geometric design with impressive accuracy. This achievement becomes even more remarkable when viewed in historical context. The temple was constructed approximately 2,600 years ago. There were no laser levels, no electronic surveying instruments, no computer modeling software, and no modern measurement devices. Yet the builders succeeded in creating a structure whose dimensions remained internally consistent across the entire layout. Modern surveys of Greek temples frequently reveal surprisingly small construction errors. In some cases, deviations are measured in mere centimeters across structures extending tens of meters. At the Parthenon, for example, researchers have documented sophisticated geometric refinements, including subtle curvature and optical corrections, designed to create visual perfection. Kardaki may represent an earlier manifestation of the same intellectual tradition. The central question is simple: how did they achieve such precision? Ancient Greek surveyors likely employed ropes, measuring rods, plumb bobs, sighting instruments, and geometric procedures derived from practical mathematics. Yet the exact methods used at Kardaki remain unknown. No construction manuals survive. No engineering drawings have been discovered. No inscriptions explain the procedures used by the architects. The precision visible in the surviving remains implies a deep understanding of geometry. To establish accurate right angles, maintain proportional relationships, and align structural elements consistently, builders required reliable measurement systems and highly trained specialists. Such expertise does not emerge spontaneously. It develops through generations of accumulated technical knowledge. Comparisons with other ancient civilizations make Kardaki even more intriguing. Egyptian pyramid builders aligned monuments with astonishing accuracy. Roman engineers constructed aqueducts that maintained gradients of only a few centimeters per kilometer. The creators of the Antikythera mechanism manufactured precision bronze gears more than 2,000 years ago. Kardaki belongs within this broader pattern of ancient technological achievement. It demonstrates that sophisticated engineering often existed long before the appearance of modern scientific instruments. The sixth mystery concerns the temple's religious purpose. Despite decades of study, archaeologists remain uncertain which deity the sanctuary was dedicated to. Various proposals have linked the temple to Apollo, Artemis, or Poseidon, but definitive evidence remains absent. This uncertainty complicates attempts to understand why the structure was built in such an unusual manner. Religious requirements often influenced architectural design in the ancient world. Without knowing the temple's exact function, researchers lack an important piece of the puzzle. In the fenlands of Lincolnshire in eastern England lies Crowland, a landscape that for centuries consisted of vast wetlands, marshes, peat bogs, and flood-prone lowlands. The ruins of Crowland Abbey dominate the area today, preserving evidence of one of medieval Britain's most remarkable engineering achievements. Historical records dating back to the 8th century describe the establishment of a religious settlement associated with St. Guthlac, while archaeological investigations conducted over the last 2 centuries have revealed foundations, water management features, masonry remains, and construction techniques that continue to puzzle researchers. The greatest mystery of Crowland begins with a simple question: why does the abbey still exist at all? Modern engineers understand the challenges of constructing large buildings on saturated ground. Soft soils compress under weight, foundations sink unevenly, and waterlogged terrain constantly shifts. Today, major projects built on unstable ground often require deep concrete piles, extending tens of meters below the surface. Yet the builders of Crowland Abbey created one of the most important monastic complexes in medieval England, in the middle of a marshland environment that should have made large-scale stone construction nearly impossible. The surviving remains indicate that the abbey was repeatedly expanded between the 11th and 15th centuries. Massive stone walls, towers, vaulted structures and supporting buildings required thousands of tons of material. Some sections of the complex rose more than 20 meters above the surrounding landscape. The problem is that the local geology was fundamentally hostile to such construction. Much of the Fenland region consists of peat deposits, silts, and waterlogged sediments that can behave almost like a sponge under heavy loads. Modern geotechnical studies show that peat-rich soils possess extremely low bearing capacity compared with bedrock. Large masonry structures built directly on such ground would normally experience severe settlement, yet Crowland survived. Archaeologists believe medieval builders may have used timber foundations, compacted gravel platforms, or carefully selected natural areas of firmer ground hidden beneath the marsh. However, no complete engineering record survives. Researchers can identify parts of the solution, but not the entire system. The situation resembles mysteries surrounding the construction of Venice, where builders drove millions of wooden piles into lagoon sediments, or the foundations of ancient Tenochtitlan in Mexico. In each case, civilizations developed specialized knowledge for building on waterlogged terrain. Crowland appears to represent a Northern European example of similar expertise. The difference is that much of Crowland's engineering knowledge vanished. Without water control, Crowland could not exist. The medieval fenlands covered thousands of square kilometers. Seasonal flooding constantly reshaped the landscape. Rivers changed course, drainage channels filled with sediment, and agricultural land could disappear beneath floodwaters. Yet Crowland became wealthy. Historical sources indicate that the abbey controlled extensive farmland, fisheries, waterways, and transportation routes. Such prosperity required sophisticated hydraulic management. The mystery lies in how accurately medieval engineers understood water behavior. Today, hydrologists rely on satellite imagery, topographic surveys, computer models, and flow simulations. Medieval builders possessed none of these tools. Nevertheless, they managed water successfully enough to support a major religious and economic center for centuries. Archaeological evidence suggests that drainage channels, embankments, and water control structures formed part of a coordinated system. Small differences in elevation, sometimes less than a meter across large distances, could determine whether land remained productive or flooded. Maintaining such systems required remarkable precision. Modern studies of reclaimed wetlands show that even minor errors in drainage gradients can drastically reduce effectiveness. Yet the medieval system functioned long before laser leveling, GPS surveying, or modern earth-moving equipment. Researchers know the system worked. What remains uncertain is exactly how its designers calculated gradients, managed seasonal fluctuations, and coordinated maintenance across a constantly changing landscape. Another puzzle concerns logistics. The abbey required enormous quantities of stone. Estimates for major medieval cathedrals and monasteries often reach tens of thousands of tons of building material. Crowland possessed no nearby mountain quarries. Stone had to be transported across difficult terrain dominated by wetlands and waterways. This raises a fascinating engineering question. How did medieval builders organize such large-scale transportation networks? Even today, transporting heavy materials through marsh environments presents challenges. Soft ground limits, wagon movement, seasonal flooding disrupts routes, and infrastructure must constantly be maintained. Researchers believe waterways probably played a crucial role. Boats and barges could move loads far more efficiently than land transport. Historical evidence from medieval England demonstrates that water transport often reduced transportation costs dramatically. However, many practical details remain unknown. How many vessels were involved? How were unloading operations conducted? How were construction schedules coordinated with seasonal river conditions? The surviving ruins demonstrate that the system worked, but the logistical mechanisms behind it remain largely invisible. In many ways, the challenge resembles the transport mysteries associated with Stonehenge, where massive stones travelled hundreds of kilometres, or the movement of granite blocks used in Egyptian pyramids. Crowland presents a medieval version of the same question. How did people without modern machinery move extraordinary quantities of material through an environment that actively resisted movement? Perhaps the most visually striking structure associated with Crowland is Trinity Bridge. Constructed around 1360, the bridge originally stood above the meeting point of multiple water channels. Unlike conventional bridges, it possesses 3 separate stairways converging at a central platform. Its unusual geometry continues to attract engineering interest. The structure effectively solved a complex transportation problem using a single stone monument instead of multiple bridges. The builders achieved this without modern structural analysis, finite element modeling, or computer calculations. Stone performs exceptionally well under compression, but poorly under tension. Medieval engineers had to design arches that distributed loads efficiently while minimizing structural weaknesses. The remarkable survival of Trinity Bridge suggests a sophisticated understanding of force distribution. Many historians compare such achievements to the great Gothic cathedrals of Europe, where master builders developed highly advanced structural solutions centuries before modern engineering theory formally described them. The bridge survives as evidence that practical engineering knowledge often preceded scientific explanation. Yet no detailed design documents survive to explain exactly how its builders calculated dimensions, load paths, or long-term durability. The masonry itself presents another mystery. Crowland Abbey contains examples of stonework that have endured weather, moisture, freeze-thaw cycles, and human conflict for centuries. Modern materials laboratories can analyze surviving mortar samples and stone composition. Researchers can identify minerals, estimate strengths, and reconstruct certain manufacturing processes. However, scientific analysis often reveals only part of the story. Construction quality depends not merely on materials but also on craftsmanship. The placement of stones, mortar preparation, curing conditions, foundation design, and structural sequencing all influence long-term durability. Many medieval master masons acquired knowledge through apprenticeship systems that transmitted techniques across generations. Unfortunately, most of that practical expertise was never written down. The phenomenon appears throughout history, Roman concrete survived for nearly 2,000 years before scientists began understanding some of the chemical processes responsible for its longevity. The mechanisms behind the Antikythera device disappeared entirely for centuries. Ancient dam builders, shipwrights and architects often left structures but not explanations. Crowland belongs to the same category of lost engineering knowledge. Large engineering projects require strong management as well as technical skill. Medieval abbey construction involved hundreds of workers across many trades and often continued for generations. Crowland raises a key question. How did administrators coordinate such complex projects without modern communication tools? Despite the lack of phones, computers, or centralized records, construction continued and expanded for centuries. The systems that made this possible remain only partly understood. Rising 575 meters above sea level on a massive limestone mountain overlooking the Isthmus of Corinth in southern Greece, the stronghold dominated one of the most strategically important corridors in the ancient Mediterranean. For more than 2,000 years, Greeks, Romans, Byzantines, Franks, Venetians, and Ottomans all occupied the same summit. Yet the greatest mystery of Acrocorinth is not its military history. It is the extraordinary engineering hidden inside the mountain itself. Beneath the walls lies evidence of ancient hydraulic systems, underground chambers, water management technology, and logistical capabilities that remain only partially understood. Modern archaeologists can map the fortress using drones, laser scanning, and digital terrain models, but many of the technical decisions made by its builders continue to puzzle researchers. Acrocorinth, known today as Acrocorinth, stands above the ancient city of Corinth in Greece. The fortress occupies the summit of a steep limestone outcrop covering roughly 3 square kilometers. Ancient authors, including Strabo and Pausanias, described the site, ensuring that its location was never truly lost. However, systematic archaeological investigation accelerated during the 19th and 20th centuries through Greek, American, and international excavations. These studies revealed that the visible walls represent only a fraction of the much older and more complex engineering landscape extending beneath the surface. The greatest engineering mystery at Acrocorinth involves water. Throughout history, mountain fortresses shared one fundamental weakness. Water supplies could be cut off during a siege. Many famous strongholds eventually surrendered not because their walls failed, but because their defenders ran out of water. Acrocorinth appears to have solved this problem. Archaeologists identified multiple cisterns, reservoirs, wells, and underground access routes connected to natural springs. The most famous is the Upper Perrine Spring, a water source carved deep into the limestone beneath the summit. Reaching the spring required descending through rock-cut stairways extending into the mountain. The engineering challenge is enormous. Limestone mountains contain highly complex underground drainage systems. Modern hydrogeologists often rely on geological surveys, drilling programs, and computer models to identify underground water pathways. Ancient builders possessed none of these tools, yet somehow they located reliable water sources with remarkable precision. Comparisons with other fortified sites reveal how unusual this achievement was. At the fortress of Masada in Israel, engineers built gigantic cistern systems to capture seasonal floods. At Acrocorinth, builders appear to have combined natural springs with artificial storage systems. This hybrid solution may have provided greater long-term reliability than many contemporary fortifications. Researchers still debate exactly how ancient engineers identified these underground water resources. Was the knowledge based on generations of geological observation? Did they recognize subtle surface indicators revealing hidden groundwater? The answer remains uncertain. beneath the fortress lies another puzzle. Numerous tunnels, stairways, chambers, and rock-cut installations penetrate deep into the limestone. Some clearly served hydraulic purposes, while others remain difficult to explain. Several underground spaces occupy locations that offer little obvious military value. They're too isolated for routine storage and too inaccessible for large-scale habitation. Some researchers propose that parts of the system originated as sacred spaces associated with earlier religious activity. Others suggest emergency shelters, hidden supply routes, or components of an unfinished hydraulic network. The problem is that the fortress evolved continuously for over 2 millennia. Greek structures were modified by Romans, Roman structures were altered by Byzantine builders, and Byzantine installations were rebuilt by Crusaders, Venetians, and Ottomans. Each phase erased evidence from earlier phases. Laser mapping has revealed architectural inconsistencies, suggesting that some underground spaces may be significantly older than the visible fortress walls. Determining their original purpose remains one of the site's most difficult archaeological challenges. Every stone at Acrocorinth presents a logistical question. The fortress walls stretch for approximately 2 kilometers around the summit. Certain defensive sectors contain massive blocks weighing several tons. All construction materials had to be transported up steep mountain slopes before being shaped and installed. Modern engineers calculate construction logistics using load capacities, transportation models, and mechanical equipment. Ancient builders relied primarily on human labor, animals, ropes, wooden sledges, and simple lifting devices. The scale becomes clearer when compared with other mountain fortifications. Transporting materials to Acrocorinth would have been significantly more difficult than building walls on level terrain such as those surrounding many Greek cities. Similar logistical challenges occurred at sites like Mycenae, Pergamon, and Masada, yet Acrocorinth's elevation made every stage of construction more demanding. Archaeologists still cannot fully reconstruct the transportation systems used during the earliest construction phases. No written manuals survive, and the engineering knowledge disappeared long ago. One of the most remarkable aspects of Acrocorinth is that its defenses seem to emerge directly from the mountain itself. Rather than forcing the landscape to conform to architecture, builders integrated architecture into the existing geology. Cliffs became walls, narrow ridges became controlled access points, and natural bottlenecks evolved into defensive choke points. Modern military analysts often describe defensive depth as one of the most effective principles of fortification. Acrocorinth demonstrates this concept centuries before formal military engineering texts discussed it systematically. Attackers advancing toward the summit faced multiple defensive zones. Each gate forced movement into predictable directions. Elevated positions provided overlapping fields of observation. Defenders could concentrate force at critical locations while exploiting gravity itself as a weapon. Some historians compare the fortress to a gigantic natural war machine. The mystery is whether this sophistication emerged gradually through centuries of adaptation, or whether the earliest planners already understood the defensive potential of the mountain with surprising precision. Perhaps the most overlooked mystery concerns endurance. Historical records indicate that Acrocorinth repeatedly survived prolonged military threats. To achieve this, the fortress required food storage, water management, sanitation systems, maintenance facilities, and organizational planning. Scientists studying ancient siege conditions estimate that an adult requires at least several liters of water daily under warm Mediterranean conditions. A garrison numbering even a few thousand individuals would therefore consume enormous quantities of water every month. The cisterns preserved at Acrocorinth suggest large-scale planning, but researchers still debate the site's maximum sustainable population during wartime. This creates a fascinating engineering problem. How did ancient administrators calculate storage requirements? How much water could the reservoirs actually hold? How long could defenders survive complete isolation? Despite extensive research, no definitive answers exist. Ancient writers described a famous sanctuary dedicated to Aphrodite occupying the summit of Acrosorint. The temple was among the most celebrated religious sites in ancient Greece, yet surprisingly little survives. Archaeologists recovered fragments, foundations, and scattered architectural remains, but the complete structure remains largely unknown. This absence creates a significant historical mystery. How could one of the most famous sanctuaries in the Greek world disappear so completely? Repeated rebuilding offers part of the explanation. Religious structures were transformed into churches, later converted into mosques, and repeatedly altered during successive occupations. Valuable stone blocks were reused in newer buildings, and earthquakes may have accelerated destruction. Nevertheless, researchers still cannot confidently reconstruct the temple's exact dimensions, architectural appearance, or engineering details. One of antiquity's most famous monuments survives primarily through texts rather than stone. El Xincal is one of the most mysterious Inca cities ever built outside Peru. Located in the Quimivil Valley of Catamarca Province, northwestern Argentina, the site lies more than 1,500 kilometers south of Cusco, the capital of the Inca Empire. Yet despite this enormous distance, archaeologists discovered a city planned according to core Inca principles, complete with a monumental ceremonial plaza, a sacred Ushnu platform, terraced hills, administrative buildings, storage facilities, and connections to the vast Chapac-Nan road network. The greatest mystery is not that the city existed, but how Inca engineers successfully recreated a sophisticated imperial center so far from the heart of their civilization while employing technologies that remain only partially understood today. The ruins became known to modern researchers during the 19th century, but systematic archaeological investigations expanded significantly during the 20th century under Argentine scholars, including Alberto Rex Gonzalez and subsequent research teams. Excavations revealed that El Xincal was likely founded during the late 15th century, possibly under the expansion campaigns of Tupac Inca Yupanqui or Huayna Capac. Covering roughly 30 hectares, the settlement quickly emerged as one of the most important Inca administrative centers in southern South America. Yet every major discovery seemed to create new questions rather than provide answers. One of the greatest engineering mysteries concerns the decision to build El Xincal itself. Most empires lose administrative control as distance increases because communication slows, transportation becomes difficult, and logistics become increasingly complex. The Roman Empire experienced these challenges, and the Han dynasty faced similar limitations. Yet the Incas successfully established a highly organized center more than 1,500 kilometers from Cusco. Without wheeled transport, iron tools, horses, or written bureaucratic records comparable to those used in Eurasian civilizations, the Inca somehow maintained authority across an empire stretching approximately 4,000 kilometers along the Andes. El Xincal demonstrates that this system worked remarkably well. Archaeologists have identified architectural layouts closely resembling those found near Cusco itself, and the precision of this replication suggests centralized planning, standardized construction methods, and highly effective communication networks. The exact mechanisms that allowed such control remain debated. Modern comparisons help illustrate the scale of this achievement. The distance separating El Xincal from Cusco is comparable to the distance between Paris and Athens, and maintaining administrative cohesion across such territory without modern communication technologies would challenge even many pre-industrial states. Perhaps the most fascinating mystery involves astronomical engineering. Several studies indicate that the city's orientation was not random. The central plaza, ceremonial structures, and surrounding sacred hills appear to interact with solar movements throughout the year. Researchers have proposed that the two prominent terraced hills flanking the city may have served as astronomical reference points. This pattern appears elsewhere in Inca architecture. Machu Picchu, Cusco, and numerous ceremonial centers contain alignments associated with solstices and equinoxes, and El Xincal seems to belong to the same tradition. The engineering challenge is significant because determining precise solar positions requires long-term observation. Modern surveyors rely on compasses, GPS systems, laser instruments, and computer models, yet Inca engineers possessed none of these technologies. Nevertheless, they achieved alignments accurate enough to remain recognizable centuries later. Some archaeologists argue that repeated observations conducted over generations allowed Inca specialists to construct reliable astronomical calendars. Others suggest that sophisticated surveying techniques may have existed but disappeared after the Spanish conquest. No definitive explanation has been established. At the center of El Xincal stands a monumental Ushnu platform. Similar structures appear throughout the Inca world, but El Xincal preserves one of the best examples discovered outside Peru. The structure appears deceptively simple, yet its position dominates the entire city. From its elevated surface, observers could view major sections of the settlement as well as surrounding natural landmarks. The mystery concerns its exact purpose. Some researchers interpret the Ushnu as a ceremonial platform used during state rituals. Others argue that it functioned as an astronomical observation point. A third hypothesis suggests that it served both political and scientific purposes simultaneously. Measurements indicate that several sightlines from the platform correspond with significant landscape features. Whether these alignments were symbolic, astronomical, administrative, or all three remains uncertain. The situation resembles debates surrounding Stonehenge in Britain and Chanquillo in Peru, where monumental structures often survive while the knowledge explaining their precise function disappears. El Xincal was not built on naturally flat ground. The settlement occupies a landscape of uneven terrain, surrounded by hills and seasonal watercourses. To create the city's organized appearance, builders modified large portions of the natural environment. Terraces were constructed, slopes were stabilized, drainage systems were established, public spaces were leveled, and ceremonial hills were reshaped. Such work required extraordinary quantities of labor. Modern engineers would employ bulldozers, excavators, grading equipment, and surveying instruments, whereas the Inca relied primarily on stone tools, wooden implements, rope, and human labor. Researchers estimate that major Inca construction projects often involved thousands of workers organized through the Emitir labor system. Yet the methods used to coordinate earth-moving operations at El Xincal remain poorly documented. The city demonstrates landscape engineering on a scale comparable to agricultural terracing systems elsewhere in the Andes, some of which moved hundreds of thousands of cubic meters of material. El Xincal may represent a similar achievement in urban planning. Water determined survival throughout the Andes. Although El Xincal receives more rainfall than many desert regions controlled by the Inca, seasonal fluctuations still created challenges. Archaeologists have identified evidence of channels, drainage features, and hydraulic planning integrated into the city's layout. The mystery lies in the sophistication of these systems. Throughout the Inca world, engineers designed water networks capable of functioning for centuries. Machu Picchu contains drainage systems that continue to operate today, while Tipon near Cusco preserves hydraulic works that remain remarkably efficient despite being more than 500 years old. El Xincal appears to have incorporated similar principles. Engineers successfully controlled runoff, protected buildings from erosion, and supplied water to critical areas of the settlement. Yet many hydraulic components remain buried or poorly understood, and future excavations may reveal a far more complex system than currently recognized. El Xincal was connected to the Hapag-Nan, the vast Inca road system extending across western South America. This network exceeded 30,000 kilometers in total length. By comparison, many major Roman roads collectively covered similar scales across Europe and the Mediterranean. The mystery is how the Inca maintained such a system without wheeled transport. Messengers known as chasqui carried information between relay stations. Goods moved through coordinated labor networks, and administrative commands traveled across mountains, deserts, and valleys. El Xincal functioned as one of the southern hubs within this immense infrastructure system. Modern logistical models suggest that maintaining reliable communication across thousands of kilometers without written dispatches should have been extremely difficult. Yet the archaeological evidence demonstrates that the system operated successfully for generations. Exactly how information, taxation records, labor obligations, and political decisions were coordinated remains one of the greatest unanswered questions in Inca studies. Only a portion of El Xincal has been thoroughly investigated. Excavations have revealed plazas, administrative compounds, ceremonial structures, and residential areas. However, large sections remain unexplored. This creates a fascinating possibility. The visible city may represent only a fraction of the original settlement. Ground-penetrating radar surveys at archaeological sites around the world have repeatedly revealed hidden architecture invisible from the surface. Similar discoveries transformed understanding of Angkor in Cambodia, Teotihuacan in Mexico, and numerous Roman cities throughout Europe. If comparable investigations are conducted extensively at El Xincal, researchers may uncover additional roads, workshops, storage facilities, elite residences, or hydraulic structures. Such discoveries could fundamentally change current interpretations of the site. Gabii is an ancient city located about 18 kilometers east of Rome in central Italy, yet its greatest mystery is not its age, but the possibility that some of the engineering principles later associated with Rome may have been developed here first. Excavations have revealed a remarkably organized urban landscape, advanced stoneworking techniques, sophisticated drainage systems, and evidence of large-scale planning dating back more than 2,500 years. The city flourished during the Iron Age and early Republican period, then gradually declined and was eventually abandoned. Unlike Rome, which was continuously rebuilt for centuries, Gabii remained relatively untouched after its collapse. As a result, archaeologists often describe it as a time capsule preserving a snapshot of urban technology from a critical stage in Mediterranean history. The site lies near the ancient volcanic basin of Lago di Castiglione in the Lazio region of Italy. Although classical writers such as Livy and Dionysius of Halicarnassus mentioned Gabii, systematic archaeological investigations only accelerated during the 20th and 21st centuries. One of the most important modern research programs, the Gabii project led by archaeologists from the University of Michigan, employed ground-penetrating radar, digital mapping, drone surveys, and large-scale excavation to reconstruct the city's layout. What researchers discovered challenged traditional assumptions about early urban development in central Italy. The first mystery concerns urban planning that appears far ahead of its time. Excavations revealed streets arranged according to a deliberate plan rather than the organic growth typically expected in early settlements. Major roads intersect at controlled angles and connect residential, industrial, and public areas in a manner resembling later Roman city planning. Some sectors display organized blocks extending across large portions of the settlement. Urban planners today recognize that creating such a layout requires surveying knowledge, standardized measurements, and administrative coordination. Similar planning is known from Greek colonies and later Roman cities, yet Gabi demonstrates that comparable concepts existed in central Italy centuries earlier than many historians once believed. Archaeologists continue to debate whether this planning emerged independently, developed through interaction with neighboring cultures, or represented an early stage of the urban traditions that would later characterize Rome itself. The second mystery involves the enormous stone industry that supported the city's construction. Gabii sat atop extensive deposits of volcanic tuff, a relatively soft rock that hardens when exposed to air. The material became one of the most important building stones in ancient Latium. Ancient quarry faces surrounding the city reveal systematic extraction on a remarkable scale. Researchers estimate that hundreds of thousands of tons of stone were removed over centuries. Large blocks were cut with surprising precision, transported across uneven terrain, and assembled into buildings, roads, walls, and drainage systems. Even today, quarrying operations require logistical planning, workforce management, transportation networks, and quality control. Yet no surviving technical documents explain how Gabii organized such a vast operation. The stone itself survives, but the engineering system that produced it remains largely invisible. The third mystery centers on construction techniques that achieved extraordinary durability. Numerous structures at Gabii survived more than 2 millennia despite earthquakes, weathering, and human activity. Walls built from carefully fitted tough blocks continue to stand in recognizable form. Modern engineers studying ancient masonry often emphasize that stability depends on load distribution, foundation preparation, block geometry, and structural balance. The builders of Gabii clearly understood these principles through experience, even if they lacked formal mathematical descriptions. Similar mysteries appear at sites such as Machu Picchu, where precisely fitted stones resist seismic activity, and at ancient Greek temples whose foundations compensated for uneven terrain. Gabii belongs to this broader category of archaeological puzzles in which successful engineering is evident, but the methods behind it remain incompletely understood. The fourth mystery is hidden underground. Beneath the visible ruins lies a network of drainage channels and water management structures that demonstrate sophisticated hydraulic knowledge. Water was one of the greatest engineering challenges of the ancient world. Too little water threatened survival, while too much damaged buildings, roads, and farmland. Excavations have revealed channels carefully designed to control runoff and direct water away from inhabited areas. Maintaining proper flow requires understanding gradients and terrain. Modern drainage engineers rely on mathematical calculations and surveying equipment. Ancient builders possessed neither laser levels nor computerized models, yet many of their systems functioned effectively for centuries. Comparable achievements can be seen in Roman aqueducts, Persian qanats, and the hydraulic networks of Angkor in Cambodia. Gabii's underground infrastructure suggests that advanced water management existed in Latium long before Rome reached its engineering peak. The fifth mystery concerns standardized housing construction. Archaeologists identified neighborhoods where multiple buildings follow similar dimensions and layouts. This pattern suggests some form of planning or building standardization. Standardization is a hallmark of complex societies because it improves efficiency simplifies construction, and facilitates maintenance. Ancient Rome eventually became famous for standardized military camps, roads, and public infrastructure. At Gabii, however, evidence indicates that certain forms of architectural standardization may have emerged centuries earlier. Researchers continue investigating whether these similarities reflect centralized planning, shared building traditions, economic constraints, or an organized administrative authority capable of coordinating large-scale construction projects. Another remarkable mystery involves the city's industrial capabilities. Excavations uncovered evidence of workshops, production zones, and economic activity integrated into the urban landscape. Ancient cities required constant supplies of tools, ceramics, building materials, and household goods. Maintaining such production demanded skilled labor, resource acquisition, transportation, and distribution systems. Comparisons with contemporary settlements suggest that Gabii functioned as more than a simple town. It operated as an economic center connected to regional trade networks throughout Latium. Yet many details of its industrial organization remain unknown. Archaeologists can identify production areas, but reconstructing the management systems behind them remains difficult because administrative records have not survived. The sixth mystery involves the relationship between Gabii and Rome. Ancient literary sources describe periods of rivalry, alliance, and cultural interaction between the two cities. Some traditions even claim that members of the Roman elite received education at Gabii. While such accounts are difficult to verify completely, archaeological evidence indicates substantial connections between the settlements. The possibility that technological, architectural, or administrative knowledge flowed from Gabii to Rome remains one of the most intriguing questions in early Italian history. Rome eventually became the largest city in the Mediterranean world, controlling an empire stretching across 3 continents. Yet during Gabii's peak, Rome was still developing. This chronological relationship raises a fascinating possibility. Some innovations later associated with Roman civilization may have roots in neighboring cities whose contributions were gradually forgotten. The seventh mystery concerns the city's sudden decline. By the imperial period, Gabii had lost much of its former importance. Population decreased, construction slowed, and major public projects ceased. Eventually, large portions of the city were abandoned. Archaeologists have proposed several explanations, including economic shifts, political centralization in Rome, changing trade routes, environmental pressures, and demographic decline. None fully explains the process. Similar mysteries surround the decline of many ancient centers, from the Maya cities of Central America to the Bronze Age settlements of the Eastern Mediterranean. Urban collapse rarely results from a single cause. Instead, it emerges from complex interactions among economic, environmental, and political factors. Gabii appears to fit this broader historical pattern, yet the precise sequence of events remains uncertain. Alinda is an ancient city located in the Aydin province of southwestern Turkey, in the historic region of Caria. Built on steep hills overlooking fertile valleys, the site occupies a strategic position roughly 30 kilometers from the ancient city of Mylassa. The ruins were first systematically documented by European explorers during the 19th century and later investigated by archaeologists studying Hellenistic urban development in Anatolia. Today, massive fortification walls, reservoirs, towers, streets, and one of the best preserved agoras in Asia Minor remain visible. Yet the greatest mystery is not what survives. It is how an ancient civilization managed to build and maintain such a sophisticated mountain city more than 2,000 years ago. The first mystery appears immediately upon entering Alinda. The city was protected by enormous defensive walls, extending across steep rocky slopes. Some surviving sections remain several meters high and hundreds of meters long. The walls follow irregular terrain with remarkable precision, adapting to cliffs, ridges and natural obstacles while maintaining defensive effectiveness. Modern engineers understand how stone fortifications work, but the mystery is how ancient builders achieved such large-scale construction in terrain that remains difficult even for modern machinery. Archaeologists estimate that many individual stone blocks weigh several tons. Thousands of these blocks were quarried, transported uphill, shaped and positioned with extraordinary accuracy. Comparisons are often made with the fortifications of Pergamon and Machu Picchu. Both sites demonstrate sophisticated adaptation to mountainous environments. Yet Olinda remains unusual because nearly the entire urban landscape was integrated into a defensive mountain system. No ancient engineering manuals survive to explain exactly how the builders organized transportation, labor management, surveying, and construction logistics on such difficult terrain. The walls remain, the methods do not. Most ancient cities developed on relatively flat ground. Olinda did not. The city was constructed across multiple elevation levels connected by terraces, retaining walls, roads, and stairways. Entire neighborhoods were effectively carved into the mountain itself. This required an understanding of geology and topography far beyond simple construction. Modern urban engineers use slope analysis, soil testing, and computer simulations before building on steep terrain. Ancient builders possessed none of these tools, yet Olinda remained occupied for centuries. Researchers continue to study how its planners calculated drainage, stabilized slopes, distributed weight across terraces, and minimized erosion. The city demonstrates a level of environmental adaptation that appears remarkably advanced for its era. Many of the retaining structures still function today despite more than 2 millennia of weathering, earthquakes, and seasonal rainfall. The precision of the planning suggests knowledge accumulated through generations of practical engineering experience. Exactly how that knowledge was transmitted remains unknown. Water represented the greatest challenge for any mountain settlement. Without a reliable supply, Olinda could never have survived. Excavations have revealed reservoirs, cisterns, channels, and hydraulic installations distributed throughout the city. These systems collected rainfall, stored water, and distributed it to residents living at different elevations. The mystery lies in scale. A substantial urban population requires enormous quantities of water. Modern estimates suggest that even modest ancient cities needed tens of thousands of liters daily for drinking, food preparation, sanitation, workshops, and military use. Researchers believe Olinda relied heavily on sophisticated rainwater harvesting systems. However, the complete hydraulic network remains only partially understood. This places Olinda among a select group of ancient sites whose water technologies continue to puzzle archaeologists, including Petra, Machu Picchu, and Masada. In each case, ancient engineers developed solutions to environmental challenges that modern researchers are still attempting to fully reconstruct. The surviving reservoirs demonstrate that the system worked. The complete design remains elusive. Among Olinda's most impressive structures stands its enormous agora. The building stretches approximately 95 meters in length and is considered one of the best preserved Hellenistic market complexes in Anatolia. At first glance, it appears to be merely a commercial structure. Closer inspection reveals a significant engineering challenge. The entire complex was constructed on uneven mountainous terrain while maintaining structural stability across a large footprint. The builders needed to create level surfaces, support substantial loads, manage drainage, and ensure long-term durability. Modern architects routinely perform complex calculations before constructing large public buildings. Ancient builders relied on geometry, observation, and practical experience. The fact that major portions of the structure survive after more than 2,000 years demonstrates that their calculations were remarkably effective. Researchers continue to debate the precise construction methods used to achieve such stability. Southwestern Anatolia lies within an active seismic region. Throughout its history, Alinda would have experienced numerous earthquakes ranging from minor tremors to major destructive events. Yet significant portions of the city remain standing. This has led some researchers to investigate whether ancient builders unintentionally developed forms of earthquake-resistant construction. Large stone blocks possess enormous mass, while carefully fitted masonry can sometimes dissipate seismic energy more effectively than rigid structures. Similar observations have been made at sites such as Sacsayhuaman in Peru, and certain Greek fortifications throughout the Mediterranean. Whether Alinda's resilience resulted from deliberate engineering or accumulated construction experience remains uncertain. What is clear is that many structures survived conditions that destroyed countless younger buildings. The city appears to embody principles of structural durability that are not yet fully understood. Ancient ruins often conceal the most important engineering achievement: logistics. Every wall, tower, reservoir, and public building required raw materials, labor, food, tools, planning, and transportation. Archaeologists estimate that constructing Alinda required moving tens of thousands of tons of stone without cranes, engines, trucks, or modern lifting equipment. The workforce needed to quarry stone, transport materials, manufacture tools, prepare foundations, and coordinate construction activities would have been enormous. Comparisons can be drawn with large-scale projects throughout the Hellenistic world. Yet, the administrative systems that organized these efforts are largely invisible in the archaeological record. How many workers participated? How were they supplied? How long did construction take? How were resources allocated? The ruins provide evidence of success, but the organizational mechanisms behind that success remain largely hidden. Rising above the Quebrada de Humahuaca Valley in Jujuy province at an elevation of approximately 2,465 meters, the settlement controlled one of the most important transportation corridors in the southern Andes. Archaeologists estimate that the site covered more than 15 hectares and contained hundreds of stone structures, storage facilities, defensive walls, ceremonial spaces, and residential districts. Built by the Omaguaca people around the 10th century CE and occupied until the Spanish conquest in the 16th century, Pucara de Tilcara remains one of the most remarkable examples of ancient engineering in South America. Yet the greatest mystery is not what survives today. The greatest mystery is how its builders acquired and applied sophisticated knowledge of military engineering, water management, logistics, and construction without leaving behind written explanations. Pucara de Tilcara is located in the Quebrada de Humahuaca, a narrow mountain valley carved by the Rio Grande in northwestern Argentina. The site became known to modern archaeology during the late 19th century, but systematic investigations began in 1908 when archaeologists Juan Bautista Ambrosetti and Salvador de Benedetti conducted extensive excavations. Their work revealed a large, fortified settlement occupying a strategic hill overlooking the valley below. Over the following decades, researchers uncovered residential compounds, defensive structures, agricultural features, storage facilities, burial areas, and evidence of long-distance trade. The discoveries transformed understanding of pre-Hispanic societies in the southern Andes and demonstrated that the region supported highly organized communities centuries before European arrival. The first mystery begins with geography. The fortress occupies a position that appears almost purpose-built for defense. From the summit, observers could monitor movement through large sections of the valley while controlling access to important trade routes linking the central Andes with lower regions farther south. Modern military historians often compare the importance of terrain selection to the placement of medieval European castles or Roman frontier forts. The builders of Pucará de Tilcara seem to have understood these principles centuries before similar concepts were formally documented in military science. The mystery is how they achieved such precision. Without modern surveying instruments, topographic maps, aerial photography, or satellite imagery, the builders identified a location that maximized visibility, defense, and control of transportation corridors simultaneously. Researchers have proposed that generations of accumulated geographic knowledge allowed the community to evaluate strategic positions with remarkable accuracy. Yet no one knows precisely how this knowledge was transmitted or organized. The fortress demonstrates a level of military planning far beyond what many people traditionally associate with pre-Columbian societies. Constructing hundreds of buildings on a steep rocky hill presented enormous engineering challenges. Unlike settlements established on flat plains, Pucará de Tilcara required extensive modification of natural terrain. Builders created artificial terraces, leveled construction platforms, stabilized slopes, and integrated architecture directly into the mountain landscape. Many structures were built using local stone without mortar. Despite centuries of weathering, earthquakes, and erosion, significant portions of the foundations remain intact. The achievement becomes even more impressive when compared with other ancient mountain settlements. Machu Picchu in Peru is famous for its terrace engineering and slope stabilization systems. Pucará de Tilcara demonstrates similar principles on a smaller scale, but under very different cultural conditions. Modern geotechnical engineers understand how slope failure occurs. They calculate load distributions, drainage patterns, and soil stability using advanced software. The Omaguaca possessed none of these technologies, yet they produced a settlement capable of surviving for centuries. How they developed this understanding remains only partially understood. Water represented one of the greatest challenges facing any settlement in the semi-arid Andes. Average rainfall in parts of the region can fluctuate dramatically from year to year. Seasonal variation creates periods of abundance followed by periods of scarcity. A large population could not survive without reliable water management. Archaeological evidence suggests that the inhabitants developed systems for collecting, directing, storing, and distributing water. However, only fragments of these systems survive. This creates a major mystery. How did thousands of people maintain a permanent settlement on an elevated hilltop where natural water access was limited? Researchers studying ancient Andean hydraulic systems often compare them to sophisticated water management networks developed by the Inca centuries later. Some scholars believe that knowledge preserved within local traditions may have contributed to later engineering developments across the Andes. The exact design of the original hydraulic infrastructure remains uncertain, leaving one of the most important technological questions unanswered. Perhaps the least visible engineering achievement at Pucará de Tilcara involved food preservation. Excavations revealed numerous storage structures capable of holding agricultural products for extended periods. Maintaining food supplies was essential because the fortress population needed protection against drought, crop failures, and military threats. The challenge was immense. Stored maize, quinoa, and other crops had to remain edible despite temperature fluctuations, insects, moisture, and microbial contamination. Modern storage facilities rely on controlled ventilation, humidity monitoring, and scientific understanding of spoilage processes. Ancient communities lacked these tools, yet evidence indicates that large-scale storage operated successfully. Some researchers suspect that architectural placement exploited prevailing winds to improve passive ventilation. Similar principles appear in ancient granaries across the Mediterranean and Middle East. Whether the Oumuagwaka independently discovered comparable solutions remains unknown. The surviving ruins suggest a sophisticated understanding of environmental control, but the details remain largely invisible. Pucara de Tilcara did not exist in isolation. Numerous archaeological sites throughout the Quebrada de Humahuaca indicate the presence of interconnected communities occupying strategically important locations. Several hilltops maintain direct lines of sight with one another. This has inspired a fascinating hypothesis. Researchers propose that visual communication systems may have linked settlements across the valley. Smoke signals, beacon fires, reflective surfaces, or other signaling methods could have transmitted warnings rapidly over long distances. History provides many parallels. The Roman Empire operated extensive beacon networks. Ancient China used signal towers along frontier defenses. Byzantine fortifications transmitted messages across mountainous terrain using fire signals. If similar systems existed here, communities could have shared information far faster than messengers traveling on foot. The problem is that communication technologies often leave little archaeological evidence. The theory remains plausible, but definitive proof has not yet been found. Northwestern Argentina lies within a tectonically active region influenced by the ongoing uplift of the Andes. Earthquakes have affected the area throughout history. Despite this reality, many structures at Pucara de Tilcara survived long enough for archaeologists to study them centuries later. Some specialists argue that the use of relatively small stones may have increased structural flexibility. Instead of resisting seismic forces through rigidity, the walls may have absorbed movement through numerous joints between individual stones. This principle resembles certain earthquake-resistant construction techniques observed elsewhere in the Andes. The comparison becomes especially interesting when examining Inca architecture. Although the construction methods differ, both traditions appear to emphasize stability through adaptive structural behavior rather than massive rigid walls. Whether the builders consciously understood seismic engineering or simply refined successful methods through generations of observation remains unknown. Either explanation implies a remarkable body of practical knowledge. A settlement of this size required more than engineering, it required organization. Archaeologists have discovered evidence of trade involving materials that originated far beyond the immediate region. Exotic goods, ceramics, and exchange networks connected the community to broader economic systems operating throughout the Andes. The logistical implications are extraordinary. Hundreds or perhaps thousands of people required food, tools, construction materials, and social coordination. Large labor projects demanded planning. Defensive infrastructure required maintenance. Agricultural production had to support both residents and specialists. Modern economists often analyze cities through models of resource distribution and labor management. Applying similar reasoning to Pucara de Tilcara reveals a surprisingly complex system operating without written bureaucratic records. The physical infrastructure survives, but the administrative mechanisms do not. This creates one of the most intriguing mysteries of all. Fonmont Castle is one of the few medieval fortresses in Britain that has remained occupied for more than 8 centuries. Located in the Vale of Glamorgan in southern Wales, the castle preserves a remarkable record of engineering knowledge dating back to the Norman period. Archaeologists can identify the stones, measure the walls, and reconstruct the different stages of construction, yet many of the techniques that enabled its builders to create such a durable structure are still not fully understood. The greatest mystery is not why the castle has survived, but how medieval builders achieved a level of structural longevity that continues to challenge modern expectations. Located approximately 15 kilometres west of Cardiff, Fonmont Castle was constructed around 1180 by the Norman St John family. Unlike many castles that became ruins after centuries of warfare and neglect, Fonmont remained continuously inhabited. This unusual history has allowed researchers to study original 12th century construction methods alongside later modifications. The castle was documented by historians for centuries, but modern archaeological investigations, architectural surveys, laser scanning projects, and conservation studies have revealed details that earlier generations could never observe. These investigations transformed Fonmont from a historic residence into a valuable laboratory for understanding medieval engineering. The most obvious mystery is durability. Parts of Fonmont's original Norman walls have survived for more than 840 years. Modern engineers often design buildings with service lives measured in decades rather than centuries. Reinforced concrete structures frequently require major repairs after 50 to 100 years. Steel components suffer corrosion, foundations shift, and materials deteriorate. Fonmont presents a very different picture. The original builders relied primarily on limestone blocks and lime mortar. Scientific studies of medieval mortars across Britain have shown that traditional lime-based materials possess remarkable flexibility compared with modern cement. Instead of resisting every movement, lime mortar can absorb small structural stresses and accommodate gradual settlement. Researchers have also discovered that some lime mortars possess limited self-healing properties, as rainwater dissolves calcium compounds and redeposits them inside microscopic cracks, partially sealing damage over time. The phenomenon resembles experimental self-healing concretes currently being developed in modern materials science laboratories. Yet medieval builders achieved similar long-term benefits without chemical engineering degrees, computerized testing equipment, or advanced laboratory analysis. The mystery is not that the walls remain standing. The mystery is how builders working in the 12th century acquired enough practical knowledge to create materials capable of surviving nearly a millennium. Modern construction projects begin with extensive geological surveys. Engineers drill boreholes, analyze soil composition, model groundwater movement, and calculate load-bearing capacities using specialized software. None of these tools existed when Fonmont was built. Yet the castle occupies a location that has proven extraordinarily stable. Despite centuries of rainfall, seasonal temperature changes, and structural modifications, the core foundations remain remarkably secure. The builder selected elevated limestone terrain that naturally resists erosion and provides excellent load-bearing support. This choice appears obvious today, but identifying such locations without modern geological science required generations of accumulated experience. Comparisons with other medieval structures reveal the importance of this decision. Numerous castles built on weaker ground experienced foundation failures, wall collapses, or extensive settlement problems, while Fonmont largely avoided such disasters. Archaeologists understand where the builders chose to build, but they do not fully understand how medieval surveyors consistently identified suitable terrain without instruments capable of measuring the subsurface conditions hidden beneath their feet. Every stone visible in Fonmont Castle had to be extracted, transported, lifted, positioned, and secured. This process sounds simple until the numbers are considered. The construction of even a relatively modest Norman stone fortress required thousands of tons of material. Every block had to move from quarry to construction site using human labour, draft animals, ropes, sledges, carts, and simple lifting devices. Modern cranes routinely lift loads weighing dozens of tons, but medieval builders relied on manpower and mechanical advantage. Historical reconstructions suggest that treadwheel cranes, pulleys, and specialized hauling systems dramatically increased lifting capacity. However, direct evidence for exactly how these systems were organized at Fondement remains scarce. The challenge becomes clearer when compared with other historical projects. Construction at castles such as the Tower of London required enormous logistical coordination. Similar organizational complexity would have been necessary at Fondement, albeit on a smaller scale. Who directed the labor force? How were materials scheduled? How were construction sequences planned? Archaeology reveals the finished product but provides only fragments of the management system that made it possible. One of the most overlooked mysteries involves measurement. Modern builders use laser levels, digital surveying equipment, GPS systems, and computer modeling, while Norman builders possessed none of these technologies. Yet surviving sections of Fondement display impressive geometric consistency. Walls remain aligned, corners remain square, and structural loads were distributed effectively enough to prevent catastrophic failure over 8 centuries. Medieval builders relied upon ropes, measuring rods, plumb bobs, wooden squares, and accumulated practical knowledge. These tools appear primitive compared with modern equipment, yet they produced results that continue to impress architectural historians. Experimental archaeology has demonstrated that skilled surveyors using only simple instruments can achieve surprising levels of accuracy. However, the exact methods employed by Fondement's builders remain uncertain because almost no technical documentation survives. The measurements are visible in stone, but the procedures that created those measurements have largely vanished. Southern Wales experiences persistent rainfall, moisture exposure, strong winds, and repeated freeze-thaw cycles. These conditions are hostile to stone architecture. Water enters microscopic cracks, freezes during cold weather, expands by approximately 9%, and gradually fractures stone from within. This process destroys buildings across the world. Yet large portions of Fondement survived century after century. The explanation appears to involve careful stone selection and intelligent drainage design. Medieval builders seem to have understood which stone layers resisted weathering most effectively. They also incorporated architectural features that directed water away from vulnerable areas. Comparisons with poorly preserved structures from the same era highlight the difference. Castles built with less durable stone often suffered severe deterioration. Fondement's builders may not have understood mineralogy in the modern scientific sense, but they clearly possessed detailed practical knowledge regarding material performance. Where that knowledge originated remains uncertain. To modern visitors, Fondement appears primarily as a historic residence. To its original builders, it was a defensive system. Every wall, doorway, elevation change, and observation point carried military significance. Medieval warfare depended heavily upon controlling movement. Defenders sought to channel attackers into predictable routes while maximizing their own tactical advantages. Military historians studying Norman castles frequently compare them to mechanical systems. Individual components served specific functions, but their effectiveness depended upon how the entire structure operated together. At Fondement, researchers can identify defensive principles, analyze sightlines, and model attack scenarios using digital simulations. What remains uncertain is how medieval military architects accumulated such sophisticated knowledge before the emergence of formal engineering schools. The castle embodies generations of battlefield experience encoded directly into architecture. The structure survives, but the educational system that produced its designers does not. Built by pre-Hispanic societies centuries before the arrival of Europeans, the site preserves stone architecture, defensive systems, agricultural infrastructure, and evidence of sophisticated engineering adapted to one of the most challenging environments in South America. Archaeologists have studied the ruins for decades, yet many of the technologies that allowed its inhabitants to construct, supply, defend, and sustain this settlement remain only partially understood. The greatest mystery is not that Fuerte Quemado existed, but how a society without modern machinery created a complex mountain stronghold whose engineering solutions continue to puzzle researchers today. Fuerte Quemado lies within the Calchaquí Valley system, a vast highland corridor stretching through northwestern Argentina. The settlement occupies elevated terrain overlooking important routes that connected communities across the Andes. Archaeological investigations conducted throughout the 20th and 21st centuries documented extensive stone structures, residential compounds, terraces, defensive walls, and evidence of long-term occupation associated with the Diaguita Calchaquí cultural sphere. The location immediately raises questions because the valley sits within a semi-arid environment where water availability is limited, temperatures fluctuate dramatically, and agricultural production requires careful environmental management. Yet the builders selected a position that provided strategic visibility over surrounding territory. Similar choices can be seen at Machu Picchu in Peru, Pucará de Tilcara in Argentina, and numerous hilltop settlements throughout the ancient Andes. However, unlike many famous sites, Fuerte Quemado remains relatively understudied, leaving numerous engineering mysteries unresolved. The first mystery concerns construction itself. At first glance, the stone buildings appear simple, but closer examination reveals a far more complex challenge. The settlement occupies uneven slopes where every structure required careful adaptation to natural terrain. Before construction could begin, builders had to create stable platforms, level foundations, and retaining systems capable of resisting erosion. Modern engineers understand the difficulty of such projects, and even today, hillside construction often requires extensive geological surveys and slope stabilization measures. Yet the inhabitants of Fuerte Quemado achieved these results using stone tools, human labor, and accumulated practical knowledge. Many walls survive despite centuries of earthquakes, seasonal rainfall, and environmental degradation. The builders appear to have understood how local rock behaved under load, how drainage affected structural stability, and how foundations should be adapted to irregular terrain. Archaeologists can document the surviving architecture, but they cannot fully reconstruct the engineering calculations or practical experience that guided construction. The settlement demonstrates expertise that clearly existed, yet the technical knowledge behind it disappeared centuries ago. Perhaps the most important engineering challenge was water. The Calchaquí valleys receive relatively low annual rainfall, and sustaining a permanent population required reliable access to water for drinking, agriculture, and livestock. Ancient Andean societies developed remarkable hydraulic technologies, including canals, reservoirs, diversion channels, and irrigation systems. Evidence suggests that communities around Fuerte Quemado participated in similar practices. Agricultural production on surrounding lands would have required careful control of seasonal water supplies, yet many original hydraulic features have either eroded away or remain buried beneath sediments. This creates a major archaeological puzzle. Researchers know that sufficient water management existed because the settlement supported a substantial population. They know agriculture was practiced because terraces and cultivated areas remain visible. However, the exact design of the hydraulic network remains unclear. The mystery resembles challenges faced at other ancient sites. At Machu Picchu, engineers constructed sophisticated drainage systems capable of handling intense rainfall. At Chaco Canyon in North America, inhabitants developed water control techniques suited to desert conditions. Fuerte Quemado appears to represent another example of environmental engineering, but many technical details remain hidden. The name Fuerte means fortress, and for good reason. The settlement occupies a naturally defensible position overlooking key approaches through the valley. Steep slopes limited access, elevated observation points provided long-range visibility, and stone walls reinforced natural barriers. The question is whether these features emerged gradually or resulted from deliberate military planning. Modern military engineers analyze terrain to maximize defensive advantages. They identify choke points, observation sectors, and vulnerable approaches. The layout of Fuerte Quemado suggests that its builders understood many of the same principles. Researchers have noted that attackers approaching the settlement would have been exposed for significant distances, while defenders positioned at higher elevations could monitor movement across large sections of the valley. Comparable defensive strategies appear in Iron Age hill forts of Europe, Inca strongholds in Peru, and desert fortifications throughout Central Asia. Yet no written records survive to explain how the designers of Fuerte Quemado developed their understanding of defensive architecture. The stones remain, but the military theory behind them does not. Every ancient monument faces the same question: how was the material moved? Although the stones at Fuerte Quemado are smaller than the massive blocks used at Sacsayhuaman or Baalbek, the total volume remains enormous. Thousands of stones had to be quarried, transported, positioned, and assembled across difficult mountain terrain. Without wheeled transport systems suitable for steep slopes, without draft animals comparable to horses or oxen, and without metal construction machinery, the builders relied primarily on human labor. This raises significant logistical questions. How many workers participated? How long did construction require? How were food supplies organized for laborers? What systems coordinated building projects across multiple generations? Archaeologists can estimate labor requirements, but the precise methods remain uncertain. Similar debates surround Stonehenge, Easter Island, and many other monumental sites. Fuerte Quemado presents the same challenge. The finished product survives, while the construction process remains largely invisible. Ancient settlements survive only if they can feed themselves. This fact makes the agricultural systems associated with Fuerte Quemado especially intriguing. The surrounding environment imposes significant limitations. Rainfall is unpredictable, soils vary considerably, and highland conditions create additional challenges. Yet archaeological evidence indicates sustained occupation over long periods. Researchers believe local populations developed sophisticated farming techniques adapted to mountain environments. Terracing likely reduced erosion, irrigation improved productivity, and crop diversification may have minimized risk during poor harvest years. The scale of organization required is remarkable. Modern studies of Andean agriculture demonstrate that terrace systems can dramatically improve water retention and soil stability. Some ancient terraces in Peru remain functional after hundreds of years, and similar principles may have been employed around Fuerte Quemado. The mystery is not whether these methods worked, because the settlement proves that they did. The mystery is how such knowledge was accumulated, transmitted, and maintained without written technical manuals. Fuerte Quemado did not exist in isolation. Artifacts recovered from settlements throughout northwestern Argentina reveal extensive regional interaction. Trade routes connected communities across valleys, mountains, and ecological zones. Goods moved between populations, and ideas likely moved as well. This introduces another technological mystery. How did engineering knowledge spread across the Andes? Today, information travels through books, universities, and digital networks. But ancient societies relied on human memory, apprenticeship, and direct communication. Yet remarkably similar solutions appear across vast regions. Hydraulic engineering, terraced agriculture, defensive planning, and stone construction techniques developed across multiple Andean cultures. Some researchers compare these exchange networks to early technology transfer systems. Skilled builders may have traveled between communities, specialists may have shared knowledge during trade interactions, and political alliances may have accelerated innovation. The evidence suggests large-scale knowledge exchange, but the exact mechanisms remain unknown. The final mystery concerns the decline of Fuerte Quemado. Like many ancient centers, Fuerte Quemado was eventually abandoned, but the exact reason remains a matter of debate. Archaeologists have proposed numerous explanations, including warfare, environmental pressures, shifting trade networks, political upheaval, population decline, and the influence of expanding regional powers. However, no single theory fully explains all of the available evidence. Quilmes ruins, high in Argentina's Calchaquí valleys at nearly 2,000 meters above sea level, should never have supported a large population. Yet for centuries, thousands of people survived, farmed, and defended themselves in one of the harshest environments in the Andes. The stones remain, the engineering remains, but the knowledge behind it does not. Located in present-day Tucumán province, Argentina, the ruins were first documented by European observers in the 19th century and later investigated through systematic archaeological studies during the 20th century. Excavations revealed one of the largest pre-Columbian settlements in Argentina, covering more than 30 hectares across a mountainside overlooking the valley below. The first mystery begins with a simple question: where did the water come from? The Calchaquí valleys are semi-arid, with average annual rainfall often less than 300 millimeters, only a fraction of what many agricultural societies receive. Yet archaeological evidence indicates that Quilmes supported a population that may have reached several thousand inhabitants during its peak. Researchers have identified canals, reservoirs, drainage systems, and agricultural infrastructure distributed throughout the settlement. Water was captured from seasonal streams and redirected across difficult terrain to cultivated areas, meaning the challenge was not merely transporting water but controlling it. Modern hydraulic engineers understand that irrigation channels require carefully calculated gradients. If the slope is too steep, erosion destroys the channel. If it is too shallow, water stagnates before reaching its destination. The surviving remains suggest that Quilmes engineers successfully maintained this balance across an extensive network without metal surveying equipment or modern mathematical instruments. Comparable hydraulic achievements are known from Inca sites such as Machu Picchu, where sophisticated drainage systems continue to function after more than 5 centuries. Yet Quilmes remains far less studied, leaving many questions unanswered regarding the exact methods used to survey and construct its water infrastructure. The city appears to grow directly out of the mountain itself. Hundreds of structures, defensive walls, storage facilities, and terraces were constructed, using locally available stone. While the material was nearby, Moving it across steep slopes presented a major engineering challenge. Unlike later colonial settlements, the builders of Quilmes had no wheeled transport systems suitable for construction. They also possessed no draft animals comparable to horses, oxen, or mules capable of hauling massive loads up mountain gradients. Archaeologists estimate that thousands of tons of stone were incorporated into the settlement over centuries of construction and expansion. The logistics involved would have required careful planning, coordinated labour, and knowledge of terrain management. This challenge resembles puzzles encountered elsewhere in the ancient world. The builders of Machu Picchu transported stone across mountain ridges, while the craters of Sacsayhuaman moved blocks weighing many tons. In every case, the structures survive while detailed records of construction techniques do not. The result is a familiar archaeological mystery. We can see what was built, but we cannot fully reconstruct how it was built. Quilmes was not merely a city, it was a defensive machine. The settlement occupied a strategic position on the mountainside, overlooking approaches through the valley. Multiple construction levels created natural defensive zones, meaning attackers advancing uphill would have been exposed to defenders positioned above them. The effectiveness of this design was demonstrated historically. The Quilmes people resisted both Inca expansion and later Spanish conquest, and historical records describe decades of resistance known as the Calchaquí Wars, among the longest indigenous resistance campaigns in South American history. What remains unclear is how the original planners selected specific defensive locations. Certain sectors provide exceptional visibility across the valley, while others appear optimized to funnel approaching forces into predictable routes. Modern military planners rely upon topographic maps, aerial imagery, and computer modeling to identify strategic positions. The engineers of Quilmes achieved remarkably similar results using only direct observation and accumulated experience. The sophistication of the defensive layout suggests a level of military engineering that remains difficult to quantify. Perhaps the greatest technological mystery of Quilmes is not its walls, its houses, or its defenses. It is agriculture. A city cannot survive without food, and water systems alone are useless unless they support agricultural production. The existence of Quilmes proves that its inhabitants solved one of the most difficult problems in ancient engineering. Producing reliable harvests in an environment where rainfall was scarce, soils were vulnerable to erosion, and temperature fluctuations could be severe. Across the mountainside, archaeologists have documented extensive agricultural terraces integrated directly into the landscape. These terraces transformed steep slopes into productive farmland, while simultaneously stabilizing soil and improving water retention. The engineering principles involved are extraordinary. Terracing reduces runoff velocity, allowing water to infiltrate soil rather than being lost downslope. It decreases erosion, conserves nutrients, and creates microclimates that can improve crop productivity. Modern agricultural science confirms the effectiveness of these techniques, and studies conducted in terraced farming regions worldwide have shown significant reductions in soil loss compared with unmodified slopes. Yet understanding why terraces work is easier than understanding how ancient builders designed them so effectively. The Quilmes engineers had no satellite imagery, no GIS software, no hydrological models, and no computerized terrain analysis. Nevertheless, they created agricultural systems capable of sustaining large populations in a semi-desert environment. Some researchers compare these achievements to the agricultural terraces of the Inca Empire, while others point to similarities with ancient terrace systems in the Mediterranean and parts of Asia. However, Quilmes developed under unique environmental conditions that required localized solutions. Several questions remain unresolved. How did the builders determine the optimal dimensions for each terrace? How did they calculate water distribution across hundreds of agricultural plots? How did they prevent catastrophic erosion during seasonal storms? How did they maintain soil fertility over generations? Evidence suggests that these systems functioned successfully for centuries. The long-term sustainability of the terraces may represent one of the most impressive examples of environmental engineering in pre-Columbian South America. Even today, researchers continue studying ancient agricultural systems to identify techniques that could help modern communities adapt to water scarcity and climate stress. In that sense, Quilmes may contain practical knowledge that remains relevant centuries after its abandonment. Producing food was only half the challenge. The inhabitants also needed to preserve it. Archaeologists have identified structures interpreted as storage facilities for agricultural products, and their placement within the settlement appears deliberate rather than random. The climate of the region creates significant temperature differences between day and night, conditions that can potentially aid preservation when storage facilities are designed correctly. Some researchers suggest that natural airflow patterns were exploited to improve ventilation and reduce spoilage. Similar passive storage principles appear in traditional systems across the Andes and Central Asia. If this interpretation is correct, the people of Quilmes possessed practical knowledge of environmental control centuries before modern refrigeration. The exact details of these storage techniques, however, remain poorly understood. The surrounding landscape offers commanding views across large sections of the valley. Several elevated points associated with the settlement may have functioned as observation stations. Archaeologists have proposed that smoke signals, fire beacons, or other visual communication methods connected Quilmes with neighboring communities. Such systems are known elsewhere in history. The Roman Empire used beacon networks, and ancient China employed signal towers along frontier regions. Similar methods could have provided early warning against approaching enemies. Unfortunately, communication technologies often leave few archaeological traces. As a result, the existence of a regional signaling network remains plausible but difficult to prove conclusively. On the edge of the Loess Plateau in northern Shanxi, China, stands evidence of a civilization that seems almost impossible to explain. More than 4,000 years ago, an unknown people constructed the largest prehistoric stone city ever discovered in East Asia, crowned by a massive stepped pyramid that remained hidden from history until the late 20th century. For decades, local villagers believed the stone ruins scattered across the hills were sections of the Great Wall. It was not until systematic archaeological investigations beginning in the 1970s and large-scale excavations after 2011 that researchers realized they had uncovered something far older. Radiocarbon dating revealed that Shimao flourished between approximately 2300 and 1800 BCE, making it contemporary with the final centuries of Egypt's Old Kingdom and the rise of the Akkadian and Sumerian civilizations in Mesopotamia. What emerged from the excavations shocked archaeologists. Instead of a small regional settlement, Shimao proved to be a vast urban center covering roughly 400 hectares, protected by massive stone walls and dominated by a gigantic stepped pyramid unlike anything previously known from prehistoric China. Before the discovery of Shimao, archaeologists believed that the earliest large urban centers of Chinese civilization were concentrated mainly in the Central Plains along the Middle Yellow River. Shimao challenged that assumption entirely. The city stood on the northern frontier of ancient China, in a region previously considered peripheral to early state development. Yet the scale of the site rivals some of the most important urban centres of its era. The fortified area enclosed approximately 4 square kilometres. Multiple defensive walls stretch for kilometres across the landscape, and tens of thousands of people may have lived within and around the city. This raises an important question. Why did one of the largest cities in East Asia emerge in a region that historians once considered marginal? Some researchers argue that Shimao controlled important trade routes connecting agricultural communities in the south with pastoral societies of the northern steppe. Others suggest access to valuable resources such as jade may have transformed the city into an economic powerhouse. However, no explanation fully accounts for the enormous concentration of labour and wealth required to construct such a settlement. The mystery becomes even more striking when compared with contemporary societies. Around the same period, many settlements elsewhere in East Asia remain relatively small, while Shimao appears to have achieved levels of social organisation far beyond what archaeologists once expected for the region. Another puzzle concerns the city's extraordinary stone architecture. Most prehistoric settlements in northern China relied heavily on rammed earth construction, and stone architecture on the scale observed at Shimao was virtually unprecedented. Archaeologists have documented extensive defensive walls constructed from carefully selected stone blocks. Some sections reach several meters in thickness and height, and the total volume of stone transported and assembled likely reached hundreds of thousands of tons. Modern engineers understand the difficulty of such projects. Quarrying stone is only the beginning. Workers must transport materials, shape blocks, stabilize foundations, and maintain structural integrity across uneven terrain. Yet no written records survive to explain how the builders organized these operations. The challenge becomes clearer when comparing Shimao with other ancient construction projects. The builders of Stonehenge transported stones weighing up to 25 tons, while Egyptian workers moved limestone blocks for the pyramids. At Shimao, an equally impressive logistical system appears to have operated, but the civilization responsible remains largely anonymous. The walls demonstrate sophisticated engineering knowledge, yet the knowledge itself has disappeared. One of the strangest discoveries at Shimao involved jade. Excavations revealed hundreds of jade artifacts deliberately embedded within sections of the city walls. In many ancient societies, jade represented prestige, wealth, and spiritual power, and such objects were normally placed in elite tombs or ceremonial contexts. At Shimao, however, valuable jade objects were literally sealed into construction materials. The purpose remains unknown. Some archaeologists interpret the practice as a ritual designed to protect the city. Others propose that jade symbolized political authority and legitimized the ruling elite. A third possibility is that the objects formed part of foundation ceremonies similar to rituals documented in later civilizations. What makes the mystery particularly important is the sheer scale of the practice. The builders sacrificed enormous quantities of valuable material for reasons that remain poorly understood. The decision suggests that engineering and religion may have been deeply intertwined within Shimao society. The greatest mystery of all rises from the center of the city. At the heart of Shimao stands a colossal stepped pyramid covering approximately 24 hectares. The structure rises about 70 meters above the surrounding landscape and consists of 11 distinct terraces stacked one above another, making it the largest known prehistoric stepped pyramid in China. The scale is astonishing. The base occupies an area comparable to dozens of modern football fields. Massive retaining walls support each terrace, while elite buildings, ceremonial spaces, and administrative complexes once occupied the upper levels. The structure transformed an entire mountain into a monumental architectural project. The engineering challenges are difficult to overstate. Building a stepped pyramid requires far more than stacking stones. Engineers must understand load distribution, slope stabilization, drainage control, and foundation reinforcement. Without these precautions, terraces collapse under their own weight. Modern geological studies indicate that the builders carefully integrated the natural topography into the design. Instead of constructing an artificial pyramid from scratch, they reshaped a hill and reinforced it using sophisticated retaining systems. This approach resembles techniques employed at certain Andean sites thousands of years later and also echoes principles observed in Mesopotamian ziggurats, where stepped platforms elevated political and religious authority above the surrounding city. Yet Shimao predates many comparable monumental projects in East Asia. Even more intriguing are the decorative elements discovered on the pyramid. Archaeologists uncovered carved stone reliefs depicting human faces, animals, and hybrid creatures. Some motifs resemble symbolic imagery that would later appear in Bronze Age Chinese cultures. This raises a profound question. Was Shimao an isolated civilization? Or was it the source of traditions that later influenced the development of Chinese civilization? The answer remains uncertain. Another mystery concerns construction logistics. Researchers estimate that moving and positioning the required stone would have demanded an enormous workforce operating over many years. The project required planning on a scale associated with early states and kingdoms. Yet no written language has been discovered at the site. The builders achieved monumental engineering without leaving behind the historical records normally associated with such achievements. The city's defences reveal another remarkable puzzle. Rather than relying on a single wall, Shimao employed multiple concentric defensive layers. Gates were positioned to restrict movement, narrow passageways created bottlenecks, and elevated observation points provided strategic visibility across the surrounding landscape. Many of these features resemble defensive concepts later used in medieval fortifications. The design suggests that warfare represented a significant concern. But who threatened such a powerful city? Archaeological evidence indicates periods of conflict, including discoveries of human skulls associated with ritual activity and possibly warfare. Yet the identity of Shimao's enemies remains unknown. The defensive system appears designed for a level of military organization rarely associated with prehistoric societies. Excavations near gateways uncovered one of the most disturbing discoveries ever made at the site. Researchers found evidence of large-scale human sacrifice, including numerous skulls believed to belong primarily to young women. Some estimates suggest that dozens of individuals may have been sacrificed during major construction phases. The practice recalls foundation sacrifices documented in various ancient civilizations. Similar rituals have been proposed for sites ranging from Mesopotamia to early dynastic China. However, the exact purpose remains uncertain. Were these offerings intended to protect the city? Were they demonstrations of political power? Or did they reflect religious beliefs that have vanished completely from history? The evidence provides clues but no definitive answers. Perhaps the greatest mystery is not how Shimao was built, but why it disappeared. Around 1800 BCE, the city was abandoned. Researchers suggest climate change, environmental stress, conflict, and political instability as possible causes, but no clear explanation exists. Despite its advanced stone construction, urban planning and engineering, the civilization vanished. History preserves the stones, but not the people who built them. Perched more than 300 metres above sea level in the Euclidean range of northeast Wales, Moel y Ger overlooks the Vale of Clwyd and commands sweeping views across northern Wales. Archaeologists believe this ancient hill fort was occupied during the Iron Age, roughly between 800 BC and the Roman conquest of Britain. At first glance, it appears to be little more than a ring of ancient earthworks on a hilltop. Yet modern surveys, excavations, and landscape analysis reveal a far more intriguing story. Hidden within its banks and ditches are clues to engineering skills, environmental knowledge, and organizational abilities that remain only partially understood. More than 2,000 years after its construction, Moel-y-Gair continues to raise questions that modern archaeology cannot fully answer. The site was recognized as an ancient monument during 19th century surveys of the Cloydian Hills, but systematic archaeological investigation developed gradually. Aerial photography, topographic mapping, geophysical surveys, and modern LiDAR scanning have since revealed details invisible from ground level. These technologies showed that Moel-y-Gair was not an isolated structure, but part of a larger network of hill forts spread across the Cloydian range. What researchers discovered was not merely a defensive enclosure, but evidence of a sophisticated understanding of terrain, construction, and regional communication. The first mystery begins with location. Modern military planners rely on satellite imagery, digital terrain models, and computer simulations to identify strategic positions. The builders of Moel-y-Gair possessed none of these technologies, yet they selected one of the most effective defensive locations in the region. From the summit, visibility extends across major natural routes running through northeast Wales, allowing anyone moving through the Vale of Clwyd to potentially be observed from the fort. Researchers studying visibility patterns have noted that the site occupies a position offering exceptional surveillance while remaining difficult to approach. This raises an obvious question. How did Iron Age builders determine the optimal location? The answer may seem simple. They climbed hills and looked around. However, choosing the best position among dozens of possible locations across a complex landscape is far more challenging than it appears. Modern viewshed analysis demonstrates that relatively small differences in elevation can dramatically affect visibility. The builder somehow identified a position that maximized observation while also providing access to water, grazing land, and transportation routes. Whether this resulted from generations of accumulated knowledge or deliberate large-scale surveying remains unknown. The second mystery involves the earthworks themselves. The defensive banks surrounding Moel-y-Gair may appear modest compared with stone fortifications such as those found in later Roman forts. Yet constructing them required an enormous amount of labor. Archaeological measurements indicate that thousands of cubic meters of earth and stone were moved to create the ramparts and ditches. Depending on the exact methods used, this could represent tens of thousands of individual labor hours. To appreciate the scale of this achievement, consider a comparison. A single cubic meter of compacted soil can weigh between 1.5 and 2 metric tons. Moving thousands of cubic meters without machinery would require a highly organized workforce. Every basket of soil had to be excavated, transported, and placed with precision. Every section of ditch required planning, and every rampart required stabilization. Yet no written instructions survive. The builders left behind the finished structure but not the engineering knowledge that created it. The third mystery concerns structural durability. Moel-y-Gair has endured more than 2 millennia of wind, rain, frost, erosion, and vegetation growth. Wales experiences some of the wettest conditions in Britain, and over centuries water gradually destroys poorly designed earthworks. Yet large portions of the fortification remain visible today. This survival suggests a sophisticated understanding of drainage and slope stability. Modern civil engineers use soil analysis, computer modeling, and geological surveys when designing large earthworks. Iron Age builders possessed none of these tools. Nevertheless, many sections of the ramparts continue to retain their form after approximately 2,000 years of exposure. How did they know which soils would remain stable? How did they manage water runoff? How did they prevent catastrophic collapse? Archaeologists can observe the results, but the practical techniques behind them remain largely speculative. The fourth mystery involves geology. Detailed surveys suggest that the builders exploited natural terrain with remarkable efficiency. Rather than imposing an artificial design onto the landscape, they integrated defensive structures into existing slopes and ridges. Steeper natural gradients were incorporated into the defensive system, reducing the amount of construction required. This approach resembles a principle used in modern military engineering: maximize natural advantages while minimizing labor costs. The problem is that such decisions require an accurate understanding of terrain. Today, engineers evaluate slope angles using instruments, whereas Iron Age builders relied entirely on observation and experience. The consistency with which hill forts across Britain exploit topography has led some researchers to argue that a sophisticated body of practical landscape knowledge once existed. If so, that knowledge disappeared long ago. The fifth mystery concerns communication. Moel Aegir was not alone. Several other hill forts occupy prominent positions along the Cloydian range, and many are visible from one another, creating the possibility of an interconnected observation network. This raises fascinating questions. Could signals have been transmitted between hill forts? Could warning messages have travelled across large distances using fire or smoke? Could communities have coordinated responses to threats through visual communication? Comparable systems existed elsewhere in the ancient world. Classical Greek states used beacon chains, Roman military forces employed signalling stations, and medieval kingdoms later developed similar warning networks. The challenge is that almost no direct evidence survives for how communication functioned in Iron Age Wales. The geography suggests the possibility, but the archaeology remains inconclusive. The sixth mystery concerns life inside the enclosure. Geophysical surveys indicate that Moel Aegir was more than a refuge used only during emergencies. Evidence suggests repeated occupation and organized activity within the fort. The arrangement of internal spaces appears structured rather than random. This raises an important question: who designed the settlement? Planning a hilltop community requires decisions about housing, storage, movement, defense, and resource management. These considerations resemble challenges faced by urban planners today, albeit on a smaller scale. The existence of organized layouts suggests that at least some individuals possessed specialized knowledge about settlement design. Yet their identities, methods, and training remain unknown. The seventh mystery involves labor organization. Archaeologists often focus on structures, but every structure represents human coordination. To build Moel Aegir, workers had to gather materials, transport resources, prepare foundations, construct defenses, and maintain the site. Food had to be supplied, tasks had to be assigned, and work had to be coordinated. Modern project management relies on written plans and records, whereas Iron Age societies relied entirely on memory and oral communication. This raises one of the most difficult questions in archaeology. How are large construction projects organized in societies that left few written documents? The answer remains elusive. The eighth mystery is the relationship between Moel Aegir and broader developments in Iron Age Britain. Across Britain, hill forts emerged during a period of significant social change. Some became political centres, others functioned as economic hubs, and a few developed into major population centres. Moel Aegir belongs to this wider phenomenon, yet its exact role remains debated. Was it primarily a fortress, a ceremonial centre, a symbol of authority, a refuge during conflict, or perhaps all of these simultaneously? Different interpretations produced very different pictures of the society that built it.